安吉县最具特色的竹建筑集群中，我感受到了归隐山林的静谧，世外桃源的美景。竹林风声起，何处染喧嚣？3、4月采茶踏青，一壶茶酒，拂袖而走。这世间纷扰，尽抛脑后。竹径一直致力于原竹建筑设计施工一体化服务，是原竹建筑行业引领者和领军企业。竹径通过策划和执行全国性大型竹建筑、竹文化活动，特别是原创和惩戒制活动，近5年来完成了200余个原竹建筑作品，原竹建筑案例和市场占有率遥遥领先。举办竹产业、竹建筑、竹文化、绿色发展高峰论坛，全国高校竹建筑设计建造大赛，北林大国际花园建造节，竹建构的无限创造分享会等全国性竹文化、竹建筑活动，以设计加科技赋能传统原竹建筑行业，既传承了传统工匠技艺，又极大推动了原竹建筑行业现代设计和科技进步。风之亭，水之亭，花海竹廊，一山一水，一竹一线，都倾注了匠人的心血。竹径拥有强大的技术研发力量，通过自主研发和与科研院校紧密合作，原竹防腐防霉处理，大幅提升原竹使用寿命。艺术不是建筑在一个伟大的观念上，而是建筑在一个小而诚实的实践上。截至2022年7月，竹径共申请专利30余项，已获得授权发明专利2项，授权实用新型专利11项。竹径掌握原竹建筑连接、支撑、功能拓展等核心技术，赋予原竹建筑全新的造型和美感。在满足功能需求的同时，通过形体塑造，使其与周遭环境融为一体。竹径通过举办全国高校竹建筑设计建造大赛和自主设计，在浙江省安吉县设计和建造了30余个竹建筑，组成了极具中国第一竹乡特色的竹建筑集群，成为泛设计圈追捧的竹建筑探寻之旅特色旅游线路。一枕竹林清风，执竿而渔，无余也乐。
湖南桃花江竹材科技股份有限公司立足于当地丰富的竹子资源，20多年专注于竹材研发、生产和应用推广，将过去用原生态的楠竹做低端的产品进行了革命性的创新，运用现代技术和机械设备进行大规模生产加工，改变了竹材的原始形态，让平常不起眼的竹子变成了可行销全球的新型高档环保新材料，颠覆了人们对竹材的传统认知。桃花江户外防腐竹材可广泛运用于高端园林景观建设，用作休闲栈道、栏杆、花架、建筑外墙装饰等，极具美观，使用性能远超防腐木和木塑复合材料，具有抗变形、不开裂和极具美观的显著特点，密度可达1.2，防腐达1级，防火达 B1级，并具有一定的抗白蚁功能。桃花江竹集成材广泛运用于地板、门窗、吊顶、背景墙、各种室内装饰、家具制造、体育用品、竹工艺品、日用品制造等各类生活用品制造，材质可与世界名贵木材相媲美。桃花江竹结构材是公司最新研制的装配式建筑新型环保材料，用作可持续发展的新型竹木建筑新领域。通过实验结果发现，建筑结构材采用集成材最为合适。经过专利技术与现代机械加工后，拥有最佳的极限承载力和弯曲母量，依旧保持着竹材优秀的物理性能，还具有吸水膨胀系数小、不易开裂和不易变形的显著优点。采用公司专利接成设备生产的竖拼竹集成材，可以一次成型10米长、1.2米宽、20毫米厚的大幅面板，支持任意裁切复合，胶合强度高，防腐防霉防火防虫，可用于户外。公司产品已应用于全国很多世界级形象工程项目，如北京冬奥会、鸟巢、行政副中心、雄安新区市民服务中心、天津滨海新区文化中心、深圳张贝郊野公园、福建海峡文化中心、西安奥体中央公园、湖南湘江新区规划展示馆。公司计划未来每年以30%以上速度增长，快速实现上市，为竹材行业发展做出贡献。
竹的王国。从熊猫食材到传统工艺，从未有人能将竹完成一次绿色工业化转型，直到竹钢的出现。竹园科技深耕于四川西南有着绿海明珠之称的洪雅县。洪雅境内竹林资源丰富，以中小径竹品种雌竹为主。雌竹生长快，韧性好，壁脆薄，纤维含量达70%以上。2011年，竹园科技因地制宜发展竹产业，依托中国林科院平台技术，研发而成多竹种重组技术产品竹钢，并将竹钢注册为商标。目前，竹园科技拥有52项专利技术，构建竹产业高科技发展新格局。竹钢高强度竹基纤维复合材料，通过定向重组炼制，竹钢强度可与玻璃钢强度比肩，它耐候性强，阻燃性高，使用寿命长，环保可再生，也能完成锯切、拼接、砂爆、上色、着油漆等多种加工方式，在异形结构建筑应用上有着巨大优势。
正在举行的世园会上，国际竹藤园首次亮相，并且首次使用了一种高性能复合材料竹钢。
通过绿色生态加工工艺制成的竹钢属于负碳产品，已取得森林认证证书，是助力双碳减排、促进绿色发展的高科技重组竹材料。竹钢可塑性强，应用极为广泛，已被应用到建筑结构、景观、地板、门窗、家具、户内外装饰以及装配式建筑等领域。当前，我国要大力发展绿色低碳产业，积极稳妥推进碳达峰、碳中和。竹钢是建筑结构与装饰一体化材料，能为建筑赋予生态竹文化的低碳科技魅力。竹生长期短，容易再生，因此竹钢是以竹代木、以竹代塑新形势下不可或缺的绿色建材。竹园科技不断创造行业的中国标准、世界标准。通过技术创新，我们发明了先进的连续式维管束分离疏解机，建成用于热压生产瓷竹板材的热压机。2021年，经权威机构鉴定，竹园科技竹钢和磨压重组竹地板均实现技术革新，产品达到国际领先水平。竹园科技坚持创新与变革，当前公司正倾力打造包含8县1院1中心在内的竹钢国际生态产业园，其中竹钢板材生产线年产可达6000吨，竹钢户外磨压地板生产线年产可达30万平方米。2022年，竹园科技还投产了竹钢深加工项目，装配式建筑加工也日趋完善。中国式现代化是人与自然和谐共生的现代化。竹园科技推动竹资源创新发展，帮助竹农增产增收。生动践行绿水青山就是金山银山，前方无法跟从，只能引领。竹园科技致力于让竹钢走出中国，走向世界，开创新型竹产业的新纪元。在这安吉县最具特色的竹建筑集群中，我感受到了归隐山林的静谧、世外桃源的美景 升起，何处染喧嚣？3、4月，采茶踏青，一壶茶酒，拂袖而走。这世间纷扰，尽抛脑后。竹径一直致力于圆竹建筑设计施工一体化服务，是圆竹建筑行业引领者和领军企业。竹径通过策划和执行全国性大型竹建筑、竹文化活动，特别是原创和惩戒制活动，近5年来完成了200余个圆竹建筑作品，圆竹建筑案例和市场占有率遥遥领先。举办竹产业、竹建筑、竹文化、绿色发展高峰论坛，全国高校竹建筑设计建造大赛，北林大国际花园建造节，竹建构的无限创造分享会等全国性竹文化、竹建筑活动，以设计加科技赋能传统圆竹建筑行业，既传承了传统工匠技艺，又极大推动了圆竹建筑行业现代设计和科技进步。风之亭，水之亭，花海竹廊，一山一水，一竹一线，都倾注了匠人的心血。竹径拥有强大的技术研发力量，通过自主研发和与科研院校紧密合作，圆竹防腐防霉处理，大幅提升圆竹使用寿命。艺术不是建筑在一个伟大的观念上，而是建筑在一个小而诚实的实践上。截至2022年7月，竹径共申请专利30余项，已获得授权发明专利2项，授权实用新型专利11项。竹径掌握圆竹建筑连接、支撑、功能拓展等核心技术，赋予圆竹建筑全新的造型和美感。在满足功能需求的同时，通过形体塑造，使其与周遭环境融为一体。竹径通过举办全国高校竹建筑设计建造大赛和自主设计，在浙江省安吉县设计和建造了30余个竹建筑，组成了极具中国第一竹乡特色的竹建筑集群，成为泛设计圈追捧的竹建筑探寻之旅特色旅游线路。一枕竹林清风，执竿而渔，无余也乐。
湖南桃花江竹材科技股份有限公司立足于当地丰富的竹子资源，20多年专注于竹材研发、生产和应用推广，将过去用原生态的楠竹做低端的产品进行了革命性的创新，运用现代技术和机械设备进行大规模生产加工，改变了竹材的原始形态，让平常不起眼的竹子变成了可行销全球的新型高档环保新材料，颠覆了人们对竹材的传统认知。桃花江户外防腐竹材可广泛运用于高端园林景观建设，用作休闲栈道、栏杆、花架、建筑外墙装饰等，极具美观，使用性能远超防腐木和木塑复合材料，具有抗变形、不开裂和极具美观的显著特点，密度可达1.2，防腐达1级，防火达 B1级，并具有一定的抗白蚁功能。桃花江竹集成材广泛运用于地板、门窗、吊顶、背景墙、各种室内装饰、家具制造、体育用品、竹工艺品、日用品制造等各类生活用品制造，材质可与世界名贵木材相媲美。桃花江竹结构材是公司最新研制的装配式建筑新型环保材料，用作可持续发展的新型竹木建筑新领域。通过实验结果发现，建筑结构材采用集成材最为合适，经过专利技术与现代机械加工后，拥有最佳的极限承载力和弯曲母量，依旧保持着竹材优秀的物理性能，还具有吸水膨胀系数小、不易开裂和不易变形的显著优点。采用公司专利接成设备生产的竖拼竹集成材，可以一次成型10米长、1.2米宽、20毫米厚的大幅面板，支持任意裁切复合，胶合强度高，防腐防霉防火防虫，可用于户外。公司产品已应用于全国很多世界级形象工程项目，如北京冬奥会、鸟巢、行政副中心、雄安新区市民服务中心、天津滨海新区文化中心、深圳张贝郊野公园、福建海峡文化中心、西安奥体中央公园、湖南湘江新区规划展示馆。公司计划未来每年以30%以上速度增长，快速实现上市，为竹材行业发展做出贡献。
将竹完成一次绿色工业化转型，直到竹钢的出现。竹园科技深耕于四川西南有着绿海明珠之称的洪雅县。洪雅境内竹林资源丰富，以中小径竹品种雌竹为主。雌竹生长快，韧性好，壁脆薄，纤维含量达70%以上。2011年，竹园科技因地制宜发展竹产业，依托中国林科院平台技术，研发而成多竹种重组技术产品竹钢，并将竹钢注册为商标。目前，竹园科技拥有52项专利技术，构建竹产业高科技发展新格局。竹钢高强度竹基纤维复合材料，通过定向重组炼制，竹钢强度可与玻璃钢强度比肩。它耐候性强，阻燃性高，使用寿命长，环保可再生，也能完成锯切、拼接、砂爆、上色、着油漆等多种加工方式，在异形结构建筑应用上有着巨大优势。
正在举行的世园会上，国际竹藤园首次亮相，并且首次使用了一种高性能复合材料竹钢。
通过绿色生态加工工艺制成的竹钢属于负碳产品，已取得森林认证证书，是助力双碳减排、促进绿色发展的高科技重组竹材料。竹钢可塑性强，应用极为广泛，已被应用到建筑结构、景观、地板、门窗、家具、户内外装饰以及装配式建筑等领域。当前，我国要大力发展绿色低碳产业，积极稳妥推进碳达峰、碳中和。竹钢是建筑结构与装饰一体化材料，能为建筑赋予生态竹文化的低碳科技魅力。竹生长期短，容易再生，因此竹钢是以竹代木、以竹代塑新形势下不可或缺的绿色建材。竹园科技不断创造行业的中国标准、世界标准。通过技术创新，我们发明了先进的连续式维管束分离疏解机，建成用于热压生产瓷竹板材的热压机。2021年，经权威机构鉴定，竹园科技竹钢和磨压重组竹地板均实现技术革新，产品达到国际领先水平。竹园科技坚持创新与变革，当前公司正倾力打造包含8县1院1中心在内的竹钢国际生态产业园，其中竹钢板材生产线年产可达6000吨，竹钢户外磨压地板生产线年产可达30万平方米。2022年，有着竹园科技还投产了竹钢深加工项目，装配式建筑加工也日趋完善。
高性能复合材料竹钢，
通过绿色生态，中国式现代化是人与自然和谐共生的现代化。竹园科技推动竹资源创新发展，帮助竹农增产增收，生动践行绿水青山就是金山银山，因为前方建筑无法跟从，只能引领。竹园科技致力于让竹钢走出中国地，走向世界门窗，开创新型竹产业的新纪元。式建筑等领域，当前我国要大力发展绿色低碳产业，积极稳妥。
在这安吉县最具特色的竹建筑集群中，
竹钢
我感受到了归隐山林的静谧，世外桃源美景，
竹文化的低碳
竹林风声起，何处染喧嚣。
因此，竹钢是
3、4月
形势下，
一壶茶酒，
绿色
拂袖而走。这世间纷扰，
科技不断
浸泡脑后。
中国标准、世界标准。通过技术创新，我们发明了先进的
逐渐一直致力于圆竹建筑设计施工一体化服务，是圆竹建筑行业引领者和领军企业。逐渐通过策划和执行全国性大型竹建筑、竹文化活动，特别是原创和惩戒制活动，近5年来完成了200余个圆竹建筑作品，圆竹建筑案例和市场占有率遥遥领先。举办竹产业、竹建筑、竹文化、绿色发展高峰论坛，全国高校竹建筑设计建造大赛，北林大国际花园建造节，竹建构的无限创造分享会等全国性竹文化、竹建筑活动，以设计加科技赋能传统圆竹建筑行业，既传承了传统工匠技艺，又极大推动了圆竹建筑行业现代设计和科技进步。风之亭，水之亭，花海竹廊，一山一水，一竹一线，都倾注了匠人的心血。竹径拥有强大的技术研发力量，通过自主研发和与科研院校紧密合作，圆竹防腐防霉处理，大幅提升圆竹使用寿命。艺术不是建筑在一个伟大的观念上，而是建筑在一个小而诚实的实践上。截至2022年7月，竹径共申请专利30余项，已获得授权发明专利2项，授权实用新型专利11项。竹径掌握圆竹建筑连接、支撑、功能拓展等核心技术，赋予圆竹建筑全新的造型和美感。在满足功能需求的同时，通过形体塑造，使其与周遭环境融为一体。竹径通过举办全国高校竹建筑设计建造大赛和自主设计，在浙江省安吉县设计和建造了30余个竹建筑，组成了极具中国第一竹乡特色的竹建筑集群，成为泛设计圈追捧的竹建筑探寻之旅特色旅游线路。一枕竹林清风，执竿而渔，无余也乐。
湖南桃花江竹材科技股份有限公司立足于当地丰富的竹子资源，20多年专注于竹材研发、生产和应用推广，将过去用原生态的楠竹做低端的产品进行了革命性的创新，运用现代技术和机械设备进行大规模生产加工，改变了竹材的原始形态，让平常不起眼的竹子变成了可行销全球的新型高档环保新材料，颠覆了人们对竹材的传统认知。桃花江户外防腐竹材可广泛运用于高端园林景观建设，用作休闲栈道、栏杆、花架、建筑外墙装饰等，极具美观，使用性能远超防腐木和木塑复合材料，具有抗变形、不开裂和极具美观的显著特点，密度可达 1.2， 防腐达1级，防火达 B1级，并具有一定的抗白蚁功能。桃花江竹集成材广泛运用于地板、门窗、吊顶、背景墙、各种室内装饰、家具制造、体育用品、竹工艺品、日用品制造等各类生活用品制造，材质可与世界名贵木材相媲美。桃花江竹结构材是公司最新研制的装配式建筑新型环保材料，用作可持续发展的新型竹木建筑新领域。通过实验结果发现，建筑结构材采用集成材最为合适，经过专利技术与现代机械加工后，拥有最佳的极限承载力和弯曲母量，依旧保持着竹材优秀的物理性能，还具有吸水膨胀系数小、不易开裂和不易变形的显著优点。采用公司专利接成设备生产的竖拼竹集成材，可以一次成型10米长、1.2米宽、20毫米厚的大幅面板，支持任意裁切复合，胶合强度高，防腐防霉防火防虫，可用于户外。公司产品已应用于全国很多世界级形象工程项目，如北京冬奥会、鸟巢、行政副中心、雄安新区市民服务中心、天津滨海新区文化中心、深圳张贝郊野公园、福建海峡文化中心、西安奥体中央公园、湖南湘江新区规划展示馆。公司计划未来每年以30%以上速度增长，快速实现上市，为竹材行业发展做出贡献。
竹的王国。从熊猫食材到传统工艺，从未有人能将竹完成一次绿色工业化转型，直到竹钢的出现。竹园科技深耕于四川西南有着绿海明珠之称的洪雅县。洪雅境内竹林资源丰富，以中小径竹品种瓷竹为主。瓷竹生长快，韧性好，壁脆薄，纤维含量达70%以上。2011年，竹园科技因地制宜发展竹产业，依托中国林科院平台技术，研发而成多竹种重组技术产品竹钢，并将竹钢注册为商标。目前，竹园科技拥有52项专利技术，构建竹产业高科技发展新格局。竹钢高强度竹基纤维复合材料，通过定向重组炼制，竹钢强度可与玻璃钢强度比肩。它耐候性强，阻燃性高，使用寿命长，环保可再生，也能完成锯切、拼接、砂爆、上色、着油漆等多种加工方式，在异形结构建筑应用上有着巨大优势。
正在举行的世园会上，国际竹藤园首次亮相，并且首次使用了一种高性能复合材料竹钢。
通过绿色生态加工工艺制成的竹钢属于负碳产品，已取得森林认证证书，是助力双碳减排、促进绿色发展的高科技重组竹材料。竹钢可塑性强，应用极为广泛，已被应用到建筑结构、景观、地板、门窗、家具、户内外装饰以及装配式建筑等领域。当前，我国要大力发展绿色低碳产业，积极稳妥推进碳达峰、碳中和。竹钢是建筑结构与装饰一体化材料，能为建筑赋予生态竹文化的低碳科技魅力。竹生长期短，容易再生，因此竹钢是以竹代木、以竹代塑新形势下不可或缺的绿色建材。竹园科技不断创造行业的中国标准、世界标准。通过技术创新，我们发明了先进的连续式维管束分离疏解机，建成用于热压生产瓷竹板材的热压机。2021年，经权威机构鉴定，竹园科技竹钢和磨压重组竹地板均实现技术革新，产品达到国际领先水平。竹园科技坚持创新与变革，当前公司正倾力打造包含8县1院1中心在内的竹钢国际生态产业园，其中竹钢板材生产线年产可达6000吨，竹钢户外磨压地板生产线年产可达30万平方米。2022年，竹园科技还投产了竹钢深加工项目，装配式建筑加工也日趋完善。中国式现代化是人与自然和谐共生的现代化。竹园科技推动竹资源创新发展，帮助竹农增产增收。生动践行绿水青山就是金山银山，前方无法跟从，只能引领。竹园科技致力于让竹钢走出中国，走向世界，开创新型竹产业的新纪元。
在这安吉县最具特色的竹建筑集群中，我感受到了归隐山林的静谧、世外桃源的美景 风升起，何处染喧嚣？3、4月，采茶踏青，一壶茶酒，拂袖而走。这世间纷扰，尽抛脑后。竹径一直致力于圆竹建筑设计施工一体化服务，是圆竹建筑行业引领者和领军企业。竹径通过策划和执行全国性大型竹建筑、竹文化活动，特别是原创和惩戒制活动，近5年来完成了200余个圆竹建筑作品，圆竹建筑案例和市场占有率遥遥领先。举办竹产业、竹建筑、竹文化、绿色发展高峰论坛，全国高校竹建筑设计建造大赛，北林大国际花园建造节，竹建构的无限创造分享会等全国性竹文化、竹建筑活动，以设计加科技赋能传统圆竹建筑行业，既传承了传统工匠技艺，又极大推动了圆竹建筑行业现代设计和科技进步。风之亭，水之亭，花海竹廊，一山一水，一竹一线，都倾注了匠人的心血。竹径拥有强大的技术研发力量，通过自主研发和与科研院校紧密合作，圆竹防腐防霉处理，大幅提升圆竹使用寿命。艺术不是建筑在一个伟大的观念上，而是建筑在一个小而诚实的实践上。截至2022年7月，竹径共申请专利30余项，已获得授权发明专利2项，授权实用新型专利11项。竹径掌握圆竹建筑连接、支撑、功能拓展等核心技术，赋予圆竹建筑全新的造型和美感。在满足功能需求的同时，通过形体塑造，使其与周遭环境融为一体。竹径通过举办全国高校竹建筑设计建造大赛和自主设计，在浙江省安吉县设计和建造了30余个竹建筑，组成了极具中国第一竹乡特色的竹建筑集群，成为泛设计圈追捧的竹建筑探寻之旅特色旅游线路。一枕竹林清风，执竿而渔，无余也乐。
湖南桃花江竹材科技股份有限公司立足于当地丰富的竹子资源，20多年专注于竹材研发、生产和应用推广，将过去用原生态的楠竹做低端的产品进行了革命性的创新，运用现代技术和机械设备进行大规模生产加工，改变了竹材的原始形态，让平常不起眼的竹子变成了可行销全球的新型高档环保新材料，颠覆了人们对竹材的传统认知。桃花江户外防腐竹材可广泛运用于高端园林景观建设，用作休闲栈道、栏杆、花架、建筑外墙装饰等，极具美观，使用性能远超防腐木和木塑复合材料，具有抗变形、不开裂和极具美观的显著特点，密度可达1.2，防腐达1级，防火达 B1级，并具有一定的抗白蚁功能。桃花江竹集成材广泛运用于地板、门窗、吊顶、背景墙、各种室内装饰、家具制造、体育用品、竹工艺品、日用品制造等各类生活用品制造，材质可与世界名贵木材相媲美。桃花江竹结构材是公司最新研制的装配式建筑新型环保材料，用作可持续发展的新型竹木建筑新领域。通过实验结果发现，建筑结构材采用集成材最为合适，经过专利技术与现代机械加工后，拥有最佳的极限承载力和弯曲母量，依旧保持着竹材优秀的物理性能，还具有吸水膨胀系数小、不易开裂和不易变形的显著优点。采用公司专利接长设备生产的竖拼竹集成材，可以一次成型10米长、1.2米宽、20毫米厚的大幅面板，支持任意裁切复合，胶合强度高，防腐防霉防火防虫，可用于户外。公司产品已应用于全国很多世界级形象工程项目，如北京冬奥会、鸟巢、行政副中心、雄安新区市民服务中心、天津滨海新区文化中心、深圳张贝郊野公园、福建海峡文化中心、西安奥体中央公园、湖南湘江新区规划展示馆。公司计划未来每年以30%以上速度增长，快速实现上市，为竹材行业发展做出贡献。
洪雅县。洪雅境内竹林资源丰富，以中小径竹品种瓷竹为主。瓷竹生长快，韧性好，壁脆薄，纤维含量达70%以上。2011年，竹园科技因地制宜发展竹产业，依托中国林科院平台技术，研发而成多竹种重组技术产品竹钢，并将竹钢注册为商标。目前，竹园科技拥有52项专利技术，构建竹产业高科技发展新格局。竹钢高强度竹基纤维复合材料，通过定向重组炼制，竹钢强度可与玻璃钢强度比肩。它耐候性强，阻燃性高，使用寿命长，环保可再生，也能完成锯切、拼接、砂爆、上色、着油漆等多种加工方式，在异形结构建筑应用上有着巨大优势。
正在举行的世园会上，国际竹藤园首次亮相，并且首次使用了一种高性能复合材料竹钢。
通过绿色生态加工工艺制成的竹钢属于负碳产品，已取得森林认证证书，是助力双碳减排、促进绿色发展的高科技重组竹材料。竹钢可塑性强，应用极为广泛，已被应用到建筑结构、景观、地板、门窗、家具、户内外装饰以及装配式建筑等领域。当前，我国要大力发展绿色低碳产业，积极稳妥推进碳达峰、碳中和。竹钢是建筑结构与装饰一体化材料，能为建筑赋予生态竹文化的低碳科技魅力。竹生长期短，容易再生，因此竹钢是以竹代木、以竹代塑新形势下不可或缺的绿色建材。竹园科技不断创造行业的中国标准、世界标准。通过技术创新，我们发明了先进的连续式维管束分离疏解机，建成用于热压生产瓷竹板材的热压机。2021年，经权威机构鉴定，竹园科技竹钢和磨压重组竹地板均实现技术革新，产品达到国际领先水平。竹园科技坚持创新与变革，当前公司正倾力打造包含8县1院1中心在内的竹钢国际生态产业园，其中竹钢板材生产线年产可达6000吨，竹钢户外磨压地板生产线年产可达30万平方米。2022年，竹园科技还投产了竹钢深加工项目，装配式建筑加工也日趋完善。中国式现代化是人与自然和谐共生的现代化。竹园科技推动竹资源创新发展，帮助竹农增产增收。生动践行绿水青山就是金山银山，前方无法跟从，只能引领。竹园科技致力于让竹钢走出中国，走向世界，开创新型竹产业的新纪元。
在这安吉县最具特色的竹建筑集群中，我感受到了归隐山林的静谧，世外桃源的美景。竹林风声起，何处染喧嚣？3、4月采茶踏青，一壶茶酒，拂袖而走。这世间纷扰，尽抛脑后。竹境一直致力于原竹建筑设计施工一体化服务， 是原竹建筑行业引领者和领军企业。竹径通过策划和执行全国性大型竹建筑、竹文化活动，特别是原创和惩戒制活动，近5年来完成了200余个原竹建筑作品，原竹建筑案例和市场占有率遥遥领先。举办竹产业、竹建筑、竹文化、绿色发展高峰论坛，全国高校竹建筑设计建造大赛，北林大国际花园建造节，竹建构的无限创造分享会等全国性竹文化、竹建筑在一个小而诚实的实践上。截至2022年7月，竹径共申请专利30余项，已获得授权发明专利2项，授权实用新型专利11项。竹径掌握原竹建筑连接、支撑、功能拓展等核心技术，赋予原竹建筑全新的造型和美感。在满足功能需求的同时，通过形体塑造，使其与周遭环境融为一体。竹径通过举办全国高校竹建筑设计建造大赛和自主设计，在浙江省安吉县设计和建造了30余个竹建筑，组成了极具中国第一竹乡特色的竹建筑集群，成为泛设计圈追捧的竹建筑探寻之旅特色旅游线路。一枕竹林清风，执竿而渔，无余也乐。
湖南桃花江竹材科技股份有限公司立足于当地丰富的竹子资源，20多年专注于竹材研发、生产和应用推广，将过去用原生态的楠竹做低端的产品进行了革命性的创新，运用现代技术和机械设备进行大规模生产加工，改变了竹材的原始形态， 让平常不起眼的竹子变成了可行销全球的新型高档环保新材料，颠覆了人们对竹材的传统认知。桃花江户外防腐竹材可广泛运用于高端园林景观建筑。桃花江竹集成材广泛运用于地板、门窗、吊顶、背景墙、各种室内装饰、家具制造、体育用品、竹工艺品、日用品制造等各类生活用品制造，材质可与世界名贵木材相媲美。桃花江竹结构材是公司最新研制的装配式建筑新型环保材料，用作可持续发展的新型竹木建筑新领域。通过实验结果发现，建筑结构材采用集成材最为合适。经过专利技术与现代机械加工后，拥有最佳的极限承载力和弯曲母量，依旧保持着竹材优秀的物理性能，还具有吸水膨胀系数小、不易开裂和不易变形的显著优点。采用公司专利接成设备生产的竖拼竹集成材，可以一次成型10米长、1.2米宽、20毫米厚的大幅面板，支持任意裁切复合，胶合强度高，防腐防霉防火防虫，可用于户外。公司产品已应用于全国很多世界级形象工程项目，如北京冬奥会、鸟巢、行政副中心、雄安新区市民服务中心、天津滨海新区文化中心、深圳张贝郊野公园、福建海峡文化中心、西安奥体中央公园、湖南湘江新区规划展示馆。公司计划未来每年以30%以上速度增长，快速实现上市，为竹材行业发展做出贡献。
将竹完成一次绿色工业化转型，直到竹钢的出现。 西南有着绿海明珠之称的洪雅县。洪雅境内竹林资源丰富，以中小径竹品种瓷竹为主。瓷竹生长快，韧性好，壁脆薄，纤维含量达70%以上。2011年，竹园科技因地制宜发展竹产业，依托中国林科院平台技术，研发而成多竹种重组技术产品竹钢，并将竹钢注册为商标。目前，竹园科技拥有52项专利技术，构建竹产业高科技发展新格局。竹钢高强度竹基纤维复合材料，通过定向重组炼制，竹钢强度可与玻璃钢强度比肩。它耐候性强，阻燃性高，使用寿命长，环保可再生，也能完成锯切、拼接、砂爆、上色、着油漆等多种加工方式，在异形结构建筑应用上有着巨大优势。
正在举行的世园会上，国际竹藤园首次亮相，并且首次使用了一种高性能复合材料竹钢。
通过绿色生态加工工艺制成的竹钢属于负碳产品，已取得森林认证证书，是助力双碳减排、促进绿色发展的高科技重组竹材料。竹钢可塑性强，应用极为广泛，已被应用到建筑结构、景观、地板、门窗、家具、户内外装饰以及装配式建筑等领域。当前，我国要大力发展绿色低碳产业，积极稳妥推进碳达峰、碳中和。竹钢是建筑结构与装饰一体化材料，能为建筑赋予生态竹文化的低碳科技魅力。竹生长期短，容易再生，因此竹钢是以竹代木、以竹代塑新形势下不可或缺的绿色建材。竹园科技不断创造行业的中国标准、世界标准。通过技术创新，我们发明了先进的连续式维管束分离疏解机，建成用于热压生产瓷竹板材的热压机。2021年，经权威机构鉴定，竹园科技竹钢和磨压重组竹地板均实现技术革新，产品达到国际领先水平。竹园科技坚持创新与变革，当前公司正倾力打造包含8县1院1中心在内的竹钢国际生态产业园，其中竹钢板材生产线年产可达6000吨，竹钢户外磨压地板生产线年产可达30万平方米。2022年，竹园科技还投产了竹钢深加工项目，装配式建筑加工也日趋完善。中国式现代化是人与自然和谐共生的现代化。竹园科技推动竹资源创新发展，帮助竹农增产增收。生动践行绿水青山就是金山银山，前方无法跟从，只能引领。竹园科技致力于让竹钢走出中国，走向世界，开创新型竹产业的新纪元。
在这安吉县最具特色的竹建筑集群中，我感受到了归隐山林的静谧，世外桃源的美景。竹林风声起，何处染喧嚣？3、4月采茶踏青，一壶茶酒，拂袖而走。这世间纷扰，尽抛脑后。竹径 一直致力于圆竹建筑设计施工一体化服务，是圆竹建筑行业引领者和领军企业。竹径通过策划和执行全国性大型竹建筑、竹文化活动，特别是原创和惩戒制活动，近5年来完成了200余个圆竹建筑作品，圆竹建筑案例和市场占有率遥遥领先。举办竹产业、竹建筑、竹文化、绿色发展高峰论坛，全国高校竹建筑设计建造大赛，北林大国际花园建造节，竹建构的无限创造分享会等全国性竹文化、竹建筑活动，以设计加科技赋能传统圆竹建筑行业，既传承了传统工匠技艺，又极大推动了圆竹建筑行业现代设计和科技进步。风之亭，水之亭，花海竹廊，一山一水，一竹一线，都倾注了匠人的心血。竹径拥有强大的技术研发力量，通过自主研发和与科研院校紧密合作，圆竹防腐防霉处理，大幅提升圆竹使用寿命。艺术不是建筑在一个伟大的观念上，而是建筑在一个小而诚实的实践上。截至2022年7月，竹径共申请专利30余项，已获得授权发明专利2项，授权实用新型专利11项。竹径掌握圆竹建筑连接、支撑、功能拓展等核心技术，赋予圆竹建筑全新的造型和美感。在满足功能需求的同时，通过形体塑造，使其与周遭环境融为一体。竹径通过举办全国高校竹建筑设计建造大赛和自主设计，在浙江省安吉县设计和建造了30余个竹建筑，组成了极具中国第一竹乡特色的竹建筑集群，成为泛设计圈追捧的竹建筑探寻之旅特色旅游线路。一枕竹林清风，执竿而渔，无语也乐。
湖南桃花江竹材科技股份有限公司立足于当地丰富的竹子资源，20多年专注于竹材研发、生产和应用推广，将过去用原生态的楠竹做低端的产品进行了革命性的创新，运用现代技术和机械设备进行大规模生产加工，改变了竹材的原始形态，让平常不起眼的竹子变成了可行销全球的新型高档环保新材料，颠覆了人们对竹材的传统认知。桃花江户外防腐竹材可广泛运用于高端园林景观建设，用作休闲栈道、栏杆、花架、建筑外墙装饰等，极具美观，使用性能远超防腐木和木塑复合材料，具有抗变形、不开裂和极具美观的显著特点，密度可达 1.2， 防腐达1级，防火达 B1级，并具有一定的抗白蚁功能。桃花江竹集成材广泛运用于地板、门窗、吊顶、背景墙、各种室内装饰、家具制造、体育用品、竹工艺品、日用品制造等各类生活用品制造，材质可与世界名贵木材相媲美。桃花江竹结构材是公司最新研制的装配式建筑新型环保材料，用作可持续发展的新型竹木建筑新领域。通过实验结果发现，建筑结构材采用集成材最为合适，经过专利技术与现代机械加工后，拥有最佳的极限承载力和弯曲母量，依旧保持着竹材优秀的物理性能，还具有吸水膨胀系数小、不易开裂和不易变形的显著优点。采用公司专利接长设备生产的竖拼竹集成材，可以一次成型10米长、1.2米宽、20毫米厚的大幅面板，支持任意裁切复合，胶合强度高，防腐防霉防火防虫，可用于户外。公司产品已应用于全国很多世界级形象工程项目，如北京冬奥会、鸟巢、行政副中心、雄安新区市民服务中心、天津滨海新区文化中心、深圳张贝郊野公园、福建海峡文化中心、西安奥体中央公园、湖南湘江新区规划展示馆。公司计划未来每年以30%以上速度增长，快速实现上市，为竹材行业发展做出贡献。
有人能将竹完成一次绿色工业化转型，直到竹钢的出现。竹园科技深耕于四川西南有着绿海明珠之称的洪雅县。洪雅境内竹林资源丰富，以中小径竹品种瓷竹为主。瓷竹生长快，韧性好，壁脆薄，纤维含量达70%以上。2011年，竹园科技因地制宜发展竹产业，依托中国林科院平台技术，研发而成多竹种重组技术产品竹钢，并将竹钢注册为商标。目前，竹园科技拥有52项专利技术，构建竹产业高科技发展新格局。竹钢高强度竹基纤维复合材料，通过定向重组炼制，竹钢强度可与玻璃钢强度比肩。它耐候性强，阻燃性高，使用寿命长，环保可再生，也能完成锯切、拼接、砂爆、上色、着油漆等多种加工方式，在异形结构建筑应用上有着巨大优势。
正在举行的世园会上，国际竹藤园首次亮相，并且首次使用了一种高性能复合材料竹钢。
通过绿色生态加工工艺制成的竹钢属于负碳产品，已取得森林认证证书，是助力双碳减排、促进绿色发展的高科技重组竹材料。竹钢可塑性强，应用极为广泛，已被应用到建筑结构、景观、地板、门窗、家具、户内外装饰以及装配式建筑等领域。当前，我国要大力发展绿色低碳产业，积极稳妥推进碳达峰、碳中和。竹钢是建筑结构与装饰一体化材料，能为建筑赋予生态竹文化的低碳科技魅力。竹生长期短，容易再生，因此竹钢是以竹代木、以竹代塑新形势下不可或缺的绿色建材。竹园科技不断创造行业的中国标准、世界标准。通过技术创新，我们发明了先进的连续式维管束分离疏解机，建成用于热压生产瓷竹板材的热压机。2021年，经权威机构鉴定，竹园科技竹钢和磨压重组竹地板均实现技术革新，产品达到国际领先水平。竹园科技坚持创新与变革，当前公司正倾力打造包含8县1院1中心在内的竹钢国际生态产业园，其中竹钢板材生产线年产可达6000吨，竹钢户外磨压地板生产线年产可达30万平方米。2022年，竹园科技还投产了竹钢深加工项目，装配式建筑加工也日趋完善。中国式现代化是人与自然和谐共生的现代化。竹园科技推动竹资源创新发展，帮助竹农增产增收。生动践行绿水青山就是金山银山，前方无法跟从，只能引领。竹园科技致力于让竹钢走出中国，走向世界，开创新型竹产业的新纪元。
在这安吉县最具特色的竹建筑集群中，我感受到了归隐山林的静谧，世外桃源的美景。竹林风声起，何处染喧嚣？ 3、4月，采茶踏青，一壶茶酒，拂袖而走。这世间纷扰，尽抛脑后。竹径一直致力于圆竹建筑设计施工一体化服务，是圆竹建筑行业引领者和领军企业。竹径通过策划和执行全国性大型竹建筑、竹文化活动，特别是原创和惩戒制活动，近5年来完成了200余个圆竹建筑作品，圆竹建筑案例和市场占有率遥遥领先。举办竹产业、竹建筑、竹文化、绿色发展高峰论坛，全国高校竹建筑设计建造大赛，北林大国际花园建造节，竹建构的无限创造分享会等全国性竹文化、竹建筑活动，以设计加科技赋能传统圆竹建筑行业，既传承了传统工匠技艺，又极大推动了圆竹建筑行业现代设计和科技进步。风之亭，水之亭，花海竹廊，一山一水，一竹一线，都倾注了匠人的心血。竹径拥有强大的技术研发力量，通过自主研发和与科研院校紧密合作，圆竹防腐防霉处理，大幅提升圆竹使用寿命。艺术不是建筑在一个伟大的观念上，而是建筑在一个小而诚实的实践上。截至2022年7月，竹径共申请专利30余项，已获得授权发明专利2项，授权实用新型专利11项。竹径掌握圆竹建筑连接、支撑、功能拓展等核心技术，赋予圆竹建筑全新的造型和美感。在满足功能需求的同时，通过形体塑造，使其与周遭环境融为一体。竹径通过举办全国高校竹建筑设计建造大赛和自主设计，在浙江省安吉县设计和建造了30余个竹建筑，组成了极具中国第一竹乡特色的竹建筑集群，成为泛设计圈追捧的竹建筑探寻之旅特色旅游线路。一枕竹林清风，执竿而渔，无余也乐。
湖南桃花江竹材科技股份有限公司立足于当地丰富的竹子资源，20多年专注于竹材研发、生产和应用推广，将过去用原生态的楠竹做低端的产品进行了革命性的创新，运用现代技术和机械设备进行大规模生产加工，改变了竹材的原始形态，让平常不起眼的竹子变成了可行销全球的新型高档环保新材料，颠覆了人们对竹材的传统认知。桃花江户外防腐竹材可广泛运用于高端园林景观建设，用作休闲栈道、栏杆、花架、建筑外墙装饰等，极具美观，使用性能远超防腐木和木塑复合材料，具有抗变形、不开裂和极具美观的显著特点，密度可达1.2，防腐达1级，防火达 B1级，并具有一定的抗白蚁功能。桃花江竹集成材广泛运用于地板、门窗、吊顶、背景墙、各种室内装饰、家具制造、体育用品、竹工艺品、日用品制造等各类生活用品制造，材质可与世界名贵木材相媲美。桃花江竹结构材是公司最新研制的装配式建筑新型环保材料，用作可持续发展的新型竹木建筑新领域。通过实验结果发现，建筑结构材采用集成材最为合适，经过专利技术与现代机械加工后，拥有最佳的极限承载力和弯曲母量，依旧保持着竹材优秀的物理性能，还具有吸水膨胀系数小、不易开裂和不易变形的显著优点。采用公司专利接成设备生产的竖拼竹集成材，可以一次成型10米长、1.2米宽、20毫米厚的大幅面板，支持任意裁切复合，胶合强度高，防腐防霉防火防虫，可用于户外。公司产品已应用于全国很多世界级形象工程项目，如北京冬奥会、鸟巢、行政副中心、雄安新区市民服务中心、天津滨海新区文化中心、深圳张贝郊野公园、福建海峡文化中心、西安奥体中央公园、湖南湘江新区规划展示馆。公司计划未来每年以30%以上速度增长，快速实现上市，为竹材行业发展做出贡献。
竹的王国。从熊猫食材到传统工艺，从未有人能将竹完成一次绿色工业化转型，直到竹钢的出现。竹园科技深耕于四川西南有着绿海明珠之称的洪雅县。洪雅境内竹林资源丰富，以中小径竹品种瓷竹为主。瓷竹生长快，韧性好，壁脆薄，纤维含量达70%以上。2011年，竹园科技因地制宜发展竹产业，依托中国林科院平台技术研发而成多竹种重组技术产品竹钢，并将竹钢注册为商标。目前，竹园科技拥有52项专利技术，构建竹产业高科技发展新格局。竹钢高强度竹基纤维复合材料，通过定向重组炼制，竹钢强度可与玻璃钢强度比肩，它耐候性强，阻燃性高，使用寿命长，环保可再生，也能完成锯切、拼接、砂爆、上色、着油漆等多种加工方式，在异形结构建筑应用上有着巨大优势。
正在举行的世园会上，国际竹藤园首次亮相，并且首次使用了一种高性能复合材料竹钢。
通过绿色生态加工工艺制成的竹钢属于负碳产品，已取得森林认证证书，是助力双碳减排、促进绿色发展的高科技重组竹材料。竹钢可塑性强，应用极为广泛，也被应用到建筑结构、景观、地板、门窗、家具、户内外装饰以及装配式建筑等领域。当前，我国要大力发展绿色低碳产业，积极稳妥推进碳达峰、碳中和。竹钢是建筑结构与装饰一体化材料，能为建筑赋予生态竹文化的低碳科技魅力。竹生长期短，容易再生，因此竹钢是以竹代木、以竹代塑新形势下不可或缺的绿色建材。竹园科技不断创造好行业的中国标准、世界标准。通过技术创新，我们发明了先进的连续式维管束分离疏解机，建成用于热压生产瓷竹板材的热压机。2021年，经权威机构鉴定，竹园科技竹钢和磨压重组竹地板均实现技术革新，产品达到国际领先水平。竹园科技坚持创新与变革，当前公司正倾力打造包含8县医院1中心在内的竹钢国际生态产业园，其中竹钢板材生产线年产可达6000吨，竹钢户外磨压地板生产线年产可达30万平方米。2022年，竹园科技还投产了竹钢深加工项目，装配式建筑加工也日趋完善。中国式现代化是人与自然和谐共生的现代化。竹园科技推动竹资源创新发展，帮助竹农增产增收。生动践行绿水青山就是金山银山，前方无法跟从，只能引领。竹园科技致力于让竹钢走出中国，走向世界，开创新型竹产业的新纪元。
在这安吉县最具特色的竹建筑集群中，我感受到了归隐山林的静谧， 景。竹林风声起，何处染喧嚣？三四月，采茶踏青，一壶茶酒，拂袖而走。这世间纷扰，尽抛脑后。竹径一直致力于圆竹建筑设计施工一体化服务，是圆竹建筑行业引领者和领军企业。竹径通过策划和执行全国性大型竹建筑、竹文化活动，特别是原创和惩戒制活动，近5年来完成了200余个圆竹建筑作品，圆竹建筑案例和市场占有率遥遥领先。举办竹产业、竹建筑、竹文化、绿色发展高峰论坛、全国高校竹建筑设计建造大赛、北林大国际花园建造节、竹建构的无限创造分享会等全国性竹文化、竹建筑活动，以设计加科技赋能传统圆竹建筑行业，既传承了传统工匠技艺，又极大推动了圆竹建筑行业现代设计和科技进步。风之亭，水之亭，花海竹廊，一山一水，一竹一线，都倾注了匠人的心血。竹径拥有强大的技术研发力量，通过自主研发和与科研院校紧密合作，圆竹防腐防霉处理，大幅提升圆竹使用寿命。艺术不是建筑在一个伟大的观念上，而是建筑在一个小而诚实的实践上。截至2022年7月，竹径共申请专利30余项，已获得授权发明专利2项，授权实用新型专利11项。竹径掌握圆竹建筑连接、支撑、功能拓展等核心技术，赋予圆竹建筑全新的造型和美感。在满足功能需求的同时，通过形体塑造，使其与周遭环境融为一体。竹径通过举办全国高校竹建筑设计建造大赛和自主设计，在浙江省安吉县设计和建造了30余个竹建筑，组成了极具中国第一竹乡特色的竹建筑集群，成为泛设计圈追捧的竹建筑探寻之旅特色旅游线路。一枕竹林清风，执竿而渔，无余也乐。
湖南桃花江竹材科技股份有限公司立足于当地丰富的竹子资源，20多年专注于竹材研发、生产和应用推广，将过去用原生态的楠竹做低端的产品进行了革命性的创新，运用现代技术和机械设备进行大规模生产加工，改变了竹材的原始形态，让平常不起眼的竹子变成了可行销全球的新型高档环保新材料，颠覆了人们对竹材的传统认知。桃花江户外防腐竹材可广泛运用于高端园林景观建设，用作休闲。湖南桃花江竹材科技股份有限公司立足于当地丰富的竹子资源，20多年专注于竹材研发、生产和应用推广，将过去用原生态的楠竹做低端的产品进行了革命性的创新，运用现代技术和机械设备进行大规模生产加工，改变了竹材的原始形态，让平常不起眼的竹子变成了可行销全球的新型高档环保新材料，颠覆了人们对竹材的传统认知。桃花江户外防腐竹材可广泛运用于高端园林景观建设，用作休闲栈道、栏杆、花架、建筑外墙装饰等，极具美观，使用性能远超防腐木和木塑复合材料，具有抗变形、不开裂和极具美观的显著特点，密度可达1.2，防腐达1级，防火达 B1级，并具有一定的抗白蚁功能。桃花江竹集成材广泛运用于地板、门窗、吊顶、背景墙、各种室内装饰、家具制造、体育用品、竹工艺品、日用品制造等各类生活用品制造，材质可与世界名贵木材相媲美。桃花江竹结构材是公司最新研制的装配式建筑新型环保材料，用作可持续发展的新型竹木建筑新领域。通过实验结果发现，建筑结构材采用集成材最为合适，经过专利技术与现代机械加工后，拥有最佳的极限承载力和弯曲母量，依旧保持着竹材优秀的物理性能，还具有吸水膨胀系数小、不易开裂和不易变形的显著优点。采用公司专利接长设备生产的竖拼竹集成材，可以一次成型10米长、1.2米宽、20毫米厚的大幅面板，支持任意裁切复合，胶合强度高，防腐防霉防火防虫，可用于户外。公司产品已应用于全国很多世界级形象工程项目，如北京冬奥会、鸟巢、行政副中心、雄安新区市民服务中心、天津滨海新区文化中心、深圳张贝郊野公园、福建海峡文化中心、西安奥体中央公园、湖南湘江新区规划展示馆。公司计划未来每年以30%以上速度增长，快速实现上市，为竹材行业发展做出贡献。
Hi, Christoph.
Hi, Kue. How are you? Good evening.
I think you can start on time.
Yes, I will.
Now over to you.
All right. Thank you so much. Hi, good evening, everybody. Good to see you again, Kue, and hi to see everybody here. Welcome, everybody, to the fourth session of the conference. The fourth session is titled Digital and Other Innovative Technologies for Designing Biocomposite Materials in Modern Constructions. We have a very tight schedule for the next 3 hours, so it'll be my job and honor and duty to keep time as tightly as possible. So with that in mind, I'll start by introducing the first speaker that we have today, which is Hannah Dahi. I hope she is present here today. So Hannah is born in Cairo, and she's a German registered architect who did her PhD at the University of Stuttgart. She's also the founder and leader of the Biomat department, Biomaterials and Material Cycles in Architecture at the University of Stuttgart since mid-2016. And she also founded and managed the Biomat at Copenhagen Research Center at Aalborg University since earlier this year in the framework of her current professorship there. She has received numerous awards and prizes and secured several research grants in the fields of material technology. So it's with great honor that I introduce her, and I look forward to her presentation, Rediscovering Our Resources and Technologies for Lighter and More Efficient Built Environment. Hannah, are you here? And can we go over to you? Hannah? I am looking across the panel here to see if I can find her.
I saw her several minutes ago.
I saw her a second ago as well. So I assume she's trying to dial back in. Nothing yet. Well, while we're waiting for her, so I'll be introducing today's session together with Professor Song-Ye Hao. We have a whole series of speakers after Hannah will be talking. We'll be hearing from Bharath Ragesh, who's going to be talking on behalf of Rodolphe Lorenzo, then Ji Li, Wei Gao, Mia Tejosaputro, I'm definitely pronouncing that in a wrong way, then later Jiang Zhang, Ying Wu, Brianna Bussinger, Esti Nurdia, and then we're going to end up with 10 minutes of Q&A. I hope that if we can stick to the timeline, we'll be able to end the session at 11 o'clock sharp. Let me see, has Hannah been able to make it to the scene yet? Not yet. Well then, Kue, I don't know if Bharath Ragesh is here.
I will.
Oh, there is Hannah. Fantastic.
Sorry. Okay.
Hannah, you made it just in time. I just gave you a quick introduction of your background and who we are seeing in front of us today. So without further ado, in order to stick to the time, I'll just give the floor directly to you. I'm very excited to see your presentation. So please share screen and take it away. You have 23 minutes.
Okay, thanks a lot for the invitation. I hope you see my screen properly and you can hear me properly as well.
Yes.
Okay. Is it now in the presentation modus?
Yes, all good.
Okay, great. So again, many thanks for the invitation. Let me have my stopwatch working. So here we go. So it's a pleasure to talk to you today about other variations within the area of bio-based materials and its application in the building construction system. And I think that the presentation has been put now after giving some info about myself. So I will skip this and we'll go directly to the topic, which is obviously very well known to you, about the impact of the building industry on the environment and why we as architects and engineers have the conscious responsibility of taking those into our account whenever we use materials and what kind of materials we're applying, and whenever we go in the design process and the means of creating new ways of approaching the building industry. And within that context, that was proposed, it was a topic of my own PhD that ended in 2014. And the main idea was to grab a further attention of what kind of alternative resources that we have in hand and to reinvestigate around them and see what are the potentials of applying them in the building industry. And within that journey, I got my first professorship in Stuttgart and created the biomed department inside the Institute of Building Structures and Structural Design, and had the idea of having the bio-based materials and material cycles in architecture, looking into the plant fibers and other means of resources that are annually renewable instead of the normal classic materials for the sake of the building industry. And then lately, through my other professorship at the University of Aalborg in Copenhagen campus in Denmark, I got the opportunity to create a linked union, which is the Biomed Copenhagen group. And at the same time, created also this year part of a company that is called Biomed TGU, and it is at the TTI GmbH, which is also having the umbrella of the University of Stuttgart. But what are we trying here to do is to merge the material properties of the new kind of material developments that we make, because we work in a bottom-up approach. And we have this as a design input within the architectural design process. And we include also the different variations of how to create form finding the geometries in a different means, depending on the material properties and also the fabrication techniques we use. And that's why I call this a design philosophy that is named materials as a design tool, because we as architects, we do not start by a geometry, but we end with it. And within that design flow, many research areas existed, including definitely composites, biocomposites, which is the topic of this session, and uniting computational design with it, reaching different kinds of lightweight structures and applying additive manufacturing technologies in many variations. Also the usage of the robotic assembly techniques, the integration of other functionalities through smart materials, biomimetics integration to have abstraction of bio-inspired structural systems, and also other kinds of biomaterials, including, for instance, mycelium. I don't know if you can see my cursor as well as moving here. So this is one of the examples like mycelium. So this is only part of the research fields we cover in biomat. And here is the team of Stuttgart, 6 PhDs, but also many master candidates and many assistants. And the team of Copenhagen is already created, and now there is one partner in it, one PhD candidate in it. And the influence of other industries to ours, like the integration of aircraft developments that is happening in the area of lightweight structures, especially in the area of composites, and also automotives and what's going on in the field, also to create lightweight structures in it, all this influenced our developments and trial to reach up to a certain innovation into our building context. Different additive manufacturing techniques, automation technologies, and also specialists from the textile industry and applying different kinds of polymers, including bioplastics, was always, we were always influenced by all those inputs. And also our work as designers and architects, that we created like our own design spaces and our own design workflows, again, reliant on having a fabrication system, like in this case, the additive manufacturing was here, 3D printing, and how we apply topology optimization stages and refine our design, include possibilities for an initial FEM, finite element modeling simulations, to know where are the deformation possibilities, to recreate our geometry and to understand its refinement possibilities. And for the case of 3D printing, we need to generate our tool paths. And at the end, the printing component here, I was examining it by sitting on it, just a very simple way of seeing if the whole composition or the structural system in that small scale is ever suitable or not. And also including other possibilities like design for disassembly, reusing the components in different geometrical constellations also is one of our approaches, and also different kind of fabrication systems that we developed further on our own or with partners like the extrusion or pultrusion, 3D printing, or tailor fiber placement, which is a technique that we investigated a lot, and we originally understood a lot of it from the colleagues from the textile fabrication industry and also the aircraft industry. Also thermoforming, preforming, filament winding, and twisted winding and lamination techniques. So different ways of how to create our own building components depending on those kind of natural fibers that are coming from either agricultural residues or jute, hemp, flax, cotton, and many others. So in this case, we created a kind of a shift paradigm, not only us, of course, but different architectural schools worldwide. But specifically in our case, we are starting by alternative materials and seeing its structural capabilities and informing the geometry, and then creating the prefabrication of the building elements, and also in one of the stages, creating the whole construction. And this is an iterative process, which is like endlessly going till we have our building. And this is just a small hint of what kind of projects that we get, and we write. Basically, I write the main idea or topic, and then have many discussions with different potential partners, and then we start going on to specifying further the idea that we want to create and investigate on, till we have a final outcome in the form of a one-to-one either construction, like what happened in the bridge project that we had with colleagues from Eindhoven. In that case, the Eindhoven colleagues were the ones who took the idea and were the main coordinator partner, and myself and Biomed team, we worked as the architects for this project, and we are making here 3 full bridges out of biocomposites with integrated sensors for structural health monitoring. And generally speaking, you will see like wide variations of ideas and examples of projects we get. They are all in the direction of integration of smart features and smart materials in the bodies of construction, and or usage of biocomposites in different ways, and so on. So this is basically our approach. And this definitely does not stop in the area of research and industrial partners, but also it goes into a level of allowing our students and master candidates to also further investigate on alternative materials, also include non-bio ones like carbon fibers, for instance, whenever this is necessary, and to include different structural capabilities like bending active possibilities to investigate on how we can start biomaterial and a fabrication system, and end by design and a new innovative solution. But specifically, bio-based materials was a topic that I took for my PhD. And one of the reasons that took me to that path is this dramatic photo that comes from 4 continents, including China and the US, and here Chile and Spain. So we see that it does not matter if this is a developing or a developed country, and if this is from which continent this comes from. This is basically a disaster that is going on worldwide, which is burning resources, burning natural fibers. And in this case, it was the rest over of the straw fibers coming out of the fields of cereals after harvesting season. And this is done, of course, informally by farmers just to empty up the field and get the land ready for the coming season, which is, of course, a dramatic issue that has a suffocation. And in many countries and in many areas, there is what is so-called black cloud phenomena, where people get almost suffocated from that. But what is a problem in a certain direction could be a potential for our field, for the building industry, because the fibers here, they are very similar in its inner composition to timber fibers, and we could do many applications out of that, which what I did in my PhD as an architect, it took my attention that there is a very high potential that we could take resources from a field and get it into ours. and through the technologies of plastic manufacturing techniques, I was able to include an elastic thermoplastic polymer and change or make a kind of composition of the fibers into an elastic or semi-elastic fiberboard that could be basically bent into so many directions that we could get. And this is like a dream for any designer to create. That we could create different applications interiorly and exteriorly, and this was patented in many parts of the world. This is basically the concept that was on a small lab scale to make the pellets and to extrude through an extrusion process this composition of the straw fibers that are recycled with a plastic composition where together bounded or compounded and extruded, but then in an upper scale that was done later in a project that was funded by the Federal Organization for Renewable Resources in Germany. An extrusion process was upscaled and we were able to create sandwich panels further. So basically this composition of the fibers and the plastics is creating the core, and we are further on reinforcing that core with veneer elements to have applications, different kind of applications. One of the applications were furniture, as seen here. Was also developed within one of our courses. So this is done by one of the students named Timo. Just forgot Timo Tsipak to include his name. And this is done within another project that was done by another a company that is lying here in Stuttgart, in the nearby on the edge of Stuttgart, in a place called Denkendorf, where the colleagues have applied after our design the same fiber board, the BioFlexi, which is the market name of this development, applied it on a large chassis or a silhouette of a hidden structure, and it proposed this idea of furniture further, and we on purpose applied on one of them this kind of coverage, and other we left it just to show the original material and how far it is flexible. And then the word was taken further, and students were given the chance to investigate also on further kind of materials and fibers. And you can see the wide variations that in each case there were different methodologies investigated of how to apply fibers in different bio-composite compositions, and also to include bio-inspired contexts like this example when a flea exoskeleton was being abstracted in one of the other courses named Biomimetics at the School of Architecture in Stuttgart with colleagues of the evolutionary biology of invertebrates at the University of Tübingen. And through the investigation on the cross-section of the flea or this insect's exoskeleton, it was seen how the fibers flow to create the bendability or the folding pattern, and all of this was integrated into the technique that is called Tailor fiber placement, where the fibers have been stitched into a similar orientation to create this kind of bending format or folding format. And this was further illustrated and applied through smaller mock-ups in this format, like it's as if it's a stool or a chair, where it was also tested by means of just sitting on it as a load and seeing its possible deformation, and it worked really perfectly. And that's another possibility of applying also the same technique I just talked about, which is the tailor fiber placement, which is that we have a stretched membrane, as you see here on the back, and we stitch the fibers onto it. And through that fiber orientation that is previously designed according to knowing how this technique works at all, the flattened pattern was created, and then it was bent into another process. And to lock it completely, filaments were winded in that 3D format, so that the creation of that structure system in the form of a stool was created. And here is the way of bending it and fixing it in position. Also, similarly, many ideas evolved, and applying short fibers and long fibers, so even short fibers with molding, short fibers with applying plastics that were extruded. We apply here thermoforming to create that silhouette and pattern, and also growing biocomposites, growing materials like mycelium, where we have rattan or bamboo or other materials that could have this level of bending and fixing that acts here as our frame, our structural frame, and then placed on it, the growing material would be on top of it. And the outcome was really fabulous, as you see, and it was many prizes were won after that development. Furthermore, as you have seen in earlier slides, that in every project, whenever there is an idea that is relatively big to compose a whole project, it was composed, and here we intended to make out of agricultural residues sandwich elements that could have integrated sound absorption and heat insulation properties. And again, this was another project with big consortium. And we went on in different developments interiorly and for partitions, flooring systems, false ceilings, and so on, till we came to a level that we investigated further on external applications like facade systems, as you see here. Here it was a project where the tailor fiber placement was being examined, and we have seen 5 different possibilities or solutions in facade systems to create solutions and also to integrate smart elements. And one of the elements is to create adaptivity. As you see here, if you can remark, there are elastic hinges, and there is, through this kind of adaptivity, a possibility to have a recreation of the shadowing system. And here is another variation of a rotational shadowing system that could have its elegant appearance in the facade system and also create a functionality. And both 2 elements, they were developed through the tailoring system to integrate adaptivity and functionality in facade elements. And also integration of automation possibilities through robotic assembly was also one of our developments, where the facade components were part of it, how to create our integrated like gripper oriented or gripper informed designs, where, for instance, here we have integrated a full opening inside the facade panel to allow our 3D printed custom head gripper to get integrated, and also through the possibility of having a slight level of bending of the natural fibers, the attachment was possible to implement. Also further on, I mean, I'm not going to talk about each individual development, but it is worth mentioning that we have exhibited in Paris with other partners from the aviation industry, and further developed to replace the epoxy completely by means of also bio-based binding materials that are originated from chitin and chitosan elements. And those are coming from exoskeletons of marine creatures and from insects, but could also come from certain kinds of mushrooms. This is also showing how far we worked on using those alternatives of the resin systems. So with this chitosan-based fluid pastes, we were able also to 3D print and investigate on that within the scope of a project that is called Team Project with a number of scientists of the University of Stuttgart, and it's still ongoing till the year 2025. And here is another project for 3D printing, but the base material here is different. It's a bioplastic, and it's filled with natural fibers of a different kind and the rest over of the timber industry. And you've seen that it is actually functioning very well. And further systems or projects that we're also working on are in the field of vertical farming. And there is a rotational system that we are trying to integrate using natural composition on the external part of facade systems. And our work here as architects, we are responsible of integrating the bio-based materials, but here they are the natural vertical farming elements into the buildings externally and integrating this with existing buildings and new construction systems. Generally speaking, our biomat developments in the form of bigger constructions like active bending lightweight shell, or this biomat pavilion up to 2018, and this freestanding mock-up, and this one as well with the different kind of units and how we implement the connection systems between them. And here is the bridge project that I already told you about. I think that I would not go in details because of time, but maybe show you, generally speaking, the developments we did so far. So the compositions that you see here were in the form of more than 370 pieces of sandwich elements of biocomposites to form this sandwich structure and create a span of more than 10 meters and a height of around 3.5 meters. And definitely the cooperation with other partners, like from the Institute of Geodesy, to have a level of punctuality and to have this very high level of having everything in the exact needed position, and to have a full quality control during construction, because we're talking about more than 370 pieces to be connected in space. And for this, we needed, of course, geodesy and, of course, structural simulation. And this is part of the team after the construction, but yeah, we were actually more than 80 people for this project. And this is one of the very largest, or the largest ever biocomposite project till now, which is a project that is covered by the Interreg, which is from the EU, one of the programs, and we are together 15 partners, 5 universities and 7 companies and 3 cities, which are the cities of Almere in Netherlands, and the city of Bergen-op Zoom, also in Netherlands, and the city of Ulm in Germany. And those are the 3 cities in which the bridges are going to be built. One was already built, which is the one in Almere that you see in the photo, and was opened on the Day of Earth this year. And the 2 others are coming very soon. The project was one of the advertised projects or shown ones in the Floriada Expo in Netherlands, and this is our basic design, and this is how basically the core of the bridge looked like. So it is basically a foam core, and wrapped all around it the flax fibers all around. And afterwards, the sensors were implemented and integrated in the body of the bridge itself to have this so-called structural health monitoring. And this is how it looked like while the balustrade was being fixed on site. And you see here how the number of partners, so all of the people here in this photo, they are not external partners. Those are even only the partners, are not even complete, but it just reflects the number of people and minds behind such development. I'm not going to go into this project in details because I can see the time, and I just want to jump on from one to one to show you how this tailoring works. That's the tailoring system, how it works, and that's the stitching process of the fiber on a stitched membrane. And I'm not going to show you the video, but just let us see the very final project that I would like you to have a look at, because it has a link to the bamboos, which is not this and not that one. Those are also for a quick info. What is this? That's a shell construction. But if you can find the connection system here, we do not use any screws or glues. Those are connections that are coming from an abstracted idea, coming from the bionic system of diatoms. The algae that is called diatoms, it has on the micro scale or even a nanoscale this kind of interlocking system. And that's the kind of system we used for this shell construction. However, this is the very final one I would like to end up with because it's linked a bit to bamboos. That's the Biomed Pavilion of last year, which we won so many prizes for it, thankfully. But the idea was to have a pultruded profile. It's again another bigger consortium with many partners, as you see. But the idea was to have something called pultrusion. Pultrusion system is a system where you have fibers in a singular orientation, and the fibers are being wetted by the binder, and we get it out of a form in the form of this pultruded profiles. And then we dealt with it as if we dealt with bamboos, but of course we know that bamboos is not internationally available. And so it is a kind of artificial bamboos in that case. And one of the major ideas was to examine how far we can bend it. And through the bending, we used the idea of the bending active structure systems. And that's what we did in our construction. So it was based on the idea of bending these linear profiles that have a very slight level of elasticity, and to fix it in position using the same lashing system that is used in the traditional bamboo construction systems, and to create through it a double curved construction system. So as you see, with the least number of complementary temporary columns, we were able to get to the level of equilibrium that we wanted. And last year in 2021, in the summer, it was possible to complete our structure system that is composed of those linear elements that are coming from pultrusion, and to use the lashing system used in the bamboo constructions to create a span of 10 meters and a height up to 4.5 meters. So you can see here through the opening ceremony, the space underneath that structure and its relevant height. And yes, actually I come to the end of my presentation. I hope that this was not a quick running and that this would be useful to you.
Thank you so much, Hannah. Fascinating work. It's a pity we don't have more time because it's beautiful work that deserves much more attention than we can give you here. There's one quick question from the room. Are you working or collaborating with the KIT or KIT? I have no idea what is meant with that, but it's a question.
Yes, they are the colleagues of Karlsruhe. Yes, they are a very nice colleague. We didn't have a specific common project in the sense we had common publications and we have so many common talks, but not yet a specific development that we did together. I hope it's coming soon.
Okay, perfect. All right. Thank you so much, Hannah. Unfortunately, we have to move on. So we're going to move on to the second presentation of tonight, which will be done by Bharath Ragesh on behalf of Rodolfo Lorenzo. I've received a small bio, which I assume is Bharath's, saying that he's a master's student at UCL, with an experience in structural engineering at Mott MacDonald, where he's been focusing on bridge design. And he has worked on various projects with several companies, including Atkins and Ramboll Engineering consultancies, on many projects related to civil infrastructure. I hope, Bharath Ragesh, you are here and that we're able to start with the presentation right away. Bharath, are you here?
Hello. Yep.
Hi. Hello. Fantastic.
Hi. Sorry,
I hope that was your profile I was just mentioning, and not.
Yep. It was me. It was me.
Okay,
it's not
perfect.
Rodolfo's.
Then take it away and share the screen and go ahead. You have 20 minutes if you can.
Yep, I'm sharing my screen.
Yes, please.
Please let me know if it's visible.
And it's visible and we hear you well. It's not yet in presentation mode. Yes, now it's all good. Thank you.
Okay. Yep. So currently, the talk I'm going to give is on a very specific part of the bamboo pole trusses that we can work on. So we have it's a very concentrated work. It's not a very diversified work as Hannah has given earlier. So this is based on a 3D frame trusses and how it could be optimized. It was my master's thesis last year, and so it was done under Dr. Rodolfo Lorenzo. He had a bigger version of how bamboo should be designed. So he had a view that how we could capture the digital design process throughout the life cycle of a bamboo, from its stage where it's being grown and up to the stage where it could be completely recycled in a digital manner. So this is what this is a part of the particular part of the process which I have worked on over here. So coming to the introduction, so the problems which we are facing in structural analysis of the bamboo pole material is that bamboo is initially, it's not a standard material. It doesn't come in a standard size or a standard strength, which we basically know. So, and the next problem is with that comes the problem with reliability. So we have a huge factor of safety, which is assigned based on testing. So compared to steel or concrete or any other construction material, we'll be having a huge factor of safeties because each member has a different stiffness and each has a different based on the material property, that is the elasticity, and also based on the cross-sectional properties, that is the area of the bamboo pole could be having various diameters within the same bamboo member, as well as the bamboo could also have varying thickness along the member. So one bamboo could have all the variations, and along with it, each and every bamboo pole will be different. So we have a lot of changes that will be coming in. So that is basically covered by the code where we have a testing standards and we have a batching process where they are clustered together and they are graded together. But still it has a significant variation. That's why it has a huge factor of safety compared to other materials which we generally design. And bamboo also requires a very high analysis effort requirement in structural process because when we make the process, like if we are checking for deflections and things like it. So each and every bamboo pole has a particular different properties. So generally we take with a standardized material when we put it in a finite element software or any analysis software. So because of that, what we generally go through is that we assume that we go for a least thickness or a standard thickness, and then we assume the member into the software, and then we check for the deflections and things. This could be quite conservative compared to what an actual scenario could be happening, because the base of the bamboo shoot is generally thicker, and as we move up in the bamboo pole, it will be somewhat thinner. So the stiffness cannot be as it is captured in the software. So that variation is generally there. So that's why there is also a need for sensitivity check, because each and every bamboo pole is different. So in a particular member, so the forces taken by them, what we assume in the software and how it happens could be quite different. So a sensitivity check is also required. Changing the materials and checking how it could affect in the analysis process. So this also causes like we could be assuming it has a particular capacity, but there could be more forces, and similarly there could be lesser forces. But it is generally covered in the codes by means of factor of safety, which is pretty high. And so coming to the next slide. So coming and looking at the material, bamboo is basically in other process. Bamboo is basically a material which is quite eco-friendly material. It captures carbon dioxide as it grows. We basically know it as a carbon sink. But bamboo structures do have some embodied carbon in the process, because we tend to process it if you're going for any other modes of construction like glue bam or any other materials which are biocomposites of bamboo. But basically even the simple bamboo poles which we use for construction could also have some associated energy and associated embodied carbon with it. So that comes out in the form of like how we construct it, how we cut it, and how it is wasted throughout its lifestyle. The wastage of the material which is being taken away, and transportation. That is also a process that we take the bamboo, it is being grown somewhere, then we process it in a particular location. And then we tend to cut it or work on it, and then again we take it for somewhere else for recycling. So these processes also have some embodied carbon associated with it. So this could be significantly reduced if we have the details of what is the diameter and what exactly do we require, instead of taking it to the side and then wasting it without the knowledge of having the database of information. So that is what the overall process which Dr. Rodolfo has given in his earlier papers, how a complete process on how a digital design methodology of how bamboos could be constructed should be used, basically. And so basically, in addition to that, optimizing the bamboo poles, which which part of the bamboo should be used on which part of the structure, could also further increase the efficiency of the structure, and similarly could even reduce further in the form of carbon dioxide emission associated with it in its life cycle. And capturing this kind of data in its lifetime, it also helps in maintenance of the structure, because we know that bamboo structures also need sort of maintenance after particular years compared to steel or concrete. So when it comes to that time, it could be easily replaced when we know what kind of strength the bamboo needs, what kind of stiffness the material needs when we have to replace it. This could be very efficient in that as well. So the background of the work is basically done by Dr. Rodolfo and Dr. Lionel Mementi. So they have given about a process where they could capture the data throughout its life cycle, and they could use it for all the processes involved in it. For one of the a few things they have specifically worked on is the measurement and testing, where Rodolfo and Mementi has written a paper on how the cross sections of the bamboo could be scanned and with a 3D scanner, and it could be converted into a proper data with a single line model or a 3D model based on the point clouds that could be further used for design of the process. It could be taken as a database. It could be a very simple industrial process as well, because you could place the bamboo as a straight material in a line in a row, and you could scan multiple bamboos and you could check it. And other thing they have worked on is also the material properties, taking into how automated it could be. So they have used a robotic arm, and they have cut various parts of the bamboo poles, and they have taken how its strength could be determined with it. So that includes elastic properties of the bamboo and also the strength of the material as well, overall shear or axial strength of the material. So in my part, I'm trying to cover the design stage, where I have tried to basically work on the finite element modeling of the process. And these data which they have taken using the cross-section, scanning of the cross-section, and also the testing the materials, this could be further used in building information modeling, because we have the exact sizes of the poles and things which we have. It could be used exactly in the structure, and with that help, you could know where the facades and other materials that comes around it could be placed in the structure. So that is the benefit we will be getting out of the first process, that is the automating of measurement and testing. And this further translates into, once we have a complete BIM model out of it, building information modeling out of it, we could use it further efficiently in construction and fabrication like any other material. We could use it for measurement for fabrication, where we could cut the bamboo poles, where we should cut it, and what diameter of material of the connections or poles what we need could be used. And same as for transportation and how efficiently it could be used. We don't have to transfer excessive materials. We could exactly transfer what we need. And further, the same BIM information could be used for the long-term life as well, because if you want to replace a particular material that has been damaged in its lifetime, we could exactly know how what is the material that has been damaged and how it could be used further. So basically, my work, I have concentrated mainly on taking a scanned bamboo pole that has been taken already by Dr. Mementi and Rodolfo, and they have scanned a bamboo pole, and they have checked it for bending properties and how they could effectively use it. So in my work, I have taken the same poles which they have taken, scanned it already, and I have found which part of the bamboo pole can be ideally used for construction. So if bamboo poles could be up to 4 meters or 8 meters in length, but our structure part can be up to 3 meters or 2 meters or whatever it is, as required for the analysis model or what it's being constructed. We cannot be sure whether we have to take the upper part or the lower part and how to effectively use it. So for that process, we have generally the scan data is taken, and it could be each and every part has been, we could analyze and check it over. So we are trying to find out which part of the member can be effectively used for which part of the structure. So if we have multiple bamboo poles, we also try to find out what is the particular, which part of the member goes together with another part of the member, because stiffness is also a very important parameter. Equivalent stiffness gives us somewhat of a behavior what we expect. If the member stiffness is a very hugely, for instance, as I have earlier mentioned, that the bottom part could be quite stout and the top part could be quite thin. So when we combine those elements, we could have a differential stiffnesses, and what we assume in an analysis could not be the same as what it behaves in the member. So those things also we try to identify over here. And the third part is again the same thing. So that is how the forces are distributed. This is basically the stiffness, which I mentioned earlier in the previous image, how it could affect us. So if we have 3 bamboos of equivalent sizes, somewhat equivalent sizes, and check it, we could have different forces on different members. This could be a property of the curvature of the bamboo, which we call it a bow or the imperfection, because bamboo is a biomaterial which could have a natural curvature compared to steel or concrete, which are pretty straight as we manufacture them. So that could induce the stiffness, that could vary the stiffness between the members. And also the cross sections. The cross section is not uniform, so overall cross section of the members could affect how much force these members could take. So coming to the overall flow chart, how we have processed this one for the modeling of the bamboo poles. So basically the input information I have taken is the coordinates of the bamboo pole, which I have got from the previous work. And the second one is the pole section properties. That is the between the internodes, that is the solid element that comes in between the diaphragms. We have taken the average cross section of the poles that we have taken up in a database format, that is a list. And the third one is this basically comes from the structure which we want to make up. So here we could take particular interval. So in our part, we have taken a member of 1 meter in length, but our bamboo poles vary from 3 to 5 meter. So 1 meter is the interval we wanted to cut the bamboo pole. So, a 3 meter bamboo pole could be cut with multiple intervals. Either you could take the bottom 1 meter, top 1 meter, or the mid 1 meter, or even you can take it, leave 100 millimeter from the bottom and then cut the next 1 meter. And similarly, you can do with other poles as well. So how we are going to cut it? So basically, we have tried to cut the bamboo pole, a single bamboo pole, into multiple intervals. So all possible intervals, or we give a particular interval where it should be cut, like 100 millimeter iteration, and the bamboo pole is cuttable into cut into all possible combinations. So we have like 5 bamboo poles, how it could be cut. So that is the first process we have done over here. And in the next one, we have indexed them. So each and every bamboo, for instance, if we have 3 meter of a bamboo pole, so excluding 1 meter, we'll have 2 meter by 0.1. That is almost 20 possible cutting that could be made over here. And in the next one, we have indexed those properties. That is, we given a name for them. And we have tried to find what are the coordinates between those members once we cut them. So we have a starting point and an ending point and the internode points. And between those internode points, what are the cross-sectional properties of the particular member? So that is also recorded over here. And after that, we try to realign the member. Realigning is nothing but the bamboo pole is not straight. So we tend to keep it in a way that it has the least eccentricity. So this is basically done with the putting it into the the weighted average method, where we have the least eccentricity between a straight line. So we found out what is the least coordinate, what is the straight line that fixes the between these points. And after that, we aligned it to 0, or the x-axis, neutral axis, so that it has the least eccentricity between the nodes and the line which is fixed at the center. And these realigned members are further analyzed because the bamboo pole has particular eccentricity between the length along the span. If I consider between 0 to 1 meter, there is an eccentricity of 0.24 meter, 0.23 meter. So this causes a particular moment. So this is analyzed over here. And after the analysis, again, based on this particular index, the forces which are coming out of the member are particularly ranked. So each and every member, we have analyzed them, and we have recorded what is the maximum stress we could get out of it, or what is the deflection, actual deflection we could get out of it. And they are recorded for further processing, actually. And after this process, we have made a case study of a single structure, that is a simple tetrahedron. And we have tried to apply forces and tried to find out what is the deflection and how it could vary by choosing various members. So that is what we have done with the case study. And the case study will be discussed further. So basically, this is what we have done. So you could see 2 planes over the left top. So that represents the starting and ending of a structural member. And all the nodes, you can see the red dots over the top line. So those are the coordinates of the bamboo pole, which could be from the starting point. So the pole is basically covered between the plane. So the coordinates and the sectional properties are basically recorded in the process. And then whatever the coordinates and the member properties have been captured over here, they're basically analyzed using finite element software, that is GSA, OSS GSA. And we have tried to find out what is the actual forces and what is the effect of this one in here. So we tried to find out what is the maximum stresses that is coming in between. Generally, if you have a straight member, we could directly say that it's P by A, that is actual force by cross-sectional area. But here we have a particular moment induced with it because of the eccentricity, because it's not straight. We have a bow in it, so that bow causes a particular moment. So we try to capture it over here. And after that, we have further, we have a database, all the members, which has like its coordinates, its properties, and then also its forces. Then we try to make a cross-section of the tetrahedron, which we have mentioned over here. So basically a straight line tetrahedron is made. And after that, we try to we already have the nodes. So these nodes have been realigned over this ones to find out what is how it could behave. So coming to the presentation, I made a simple video of how it works. So this is the member length. So we have taken the length of 1 meter over there. And then we have made it as a time loop. So Grasshopper does not have a for loop that could record from start to end. The start cannot be completed with the end. So this is the pole that has been moved over the surfaces that has been moved. And the start nodes, the end nodes, and the nodes in between have been captured between those nodes actually over here. And those are recorded further over here. And their cross sections are also recorded over here. And after that, so this is basically the time loop which I was mentioning. And further, this is the realigning process where we have again made a time loop, and we have run all the possible combinations which we have generated out of these poles. And we have run it each and every coordinates which we get out of the straight this intersections. It has been made more straighter, that is between aligned it with respect to the x-axis. That's what we have done over here. So this will be this will have a minimum eccentricity compared to making them somewhat, if it starts from 0 and then ends at 0.3, it will have a more eccentricity and it could give a higher effect. While it starts with respect to minimum 0 and it almost ends with 0, it will have a more straighter effect over there. And here we have run each and every member with respect to in GSA. So this is external software that is run in Grasshopper. And here we have found out what is the stresses that is coming out of it, what is the actual forces and deflections that is coming out of it. And we have recorded it for each and every member. The 5 members are basically the stresses are coming out of the moments. And the bottom 3 are the axial and transverse deflections with respect to both the directions along the length of the poles. So that has been performed over here. So this is basically saved in a GSA file over here for recording. So the same file is used again and again inside Grasshopper, and a clear database is made out of it. So that's what has been performed over here. And so after that, this is the process where we have ranked the members. So again, we got the members which have been analyzed for stresses and forces. Here we have ranked them based on what is the least stresses that is coming out of the member, and what is the member index that has the least stresses, and what are the member index that develops the maximum stresses for in the same bamboo pole. And they have been ranked over here. And the same has been, it's not only been done on stresses, but we have also checked it for axial deflections and also deflection in Y and Z direction, that is the transverse deflections along the length of the member. So they are ranked for the particular index, and these ranking can be further used for a case study. So this is what we have done over here. And coming to the case study file, we have basically, initially we have developed a simple tetrahedron with a straight line cross section with the minimum cross section of a straight line with the minimum cross sections over here. And this has been analyzed, and we have found out what is the deflection this causes. And after that, this has been compared with all possible combinations, which we'll be further discussing in the further slides. So this is the cross section that has been created with the the bow of the bamboo into the effect. That is the non-linearity. It's not a straight line. Those effect has been captured over here. This is the same lines between the same points are used, but the 1 meter poles are realigned over these nodes so that they can be used further, and how it could be done. So this could be further done for an entire structure where we could make an entire structure out of the lines, and we could just realign the lines and make a truss easily out of the same members actually over here. So this has been performed over here. And the corresponding forces, that is, we have taken the top node over here. We have found out what is the maximum vertical deflections, and we have studied what is the transverse deflections in the bottom nodes as well. So that is a study we have performed in this one. So coming to the next one. So these are the cases which we have studied. So what kind of members can be combined? So we know that we have the actual data of the poles and each and every pole, but we don't know what members we have to use over here. So for that, we have used the first one we have used is the generic member of the pole, and the second one we have used members with the least wastage. That is, the first pole is the first pole, and the next immediate pole will be used. And the third one we have taken based on the least stresses. Fourth one based with the least axial stresses that is being developed. The fifth one with the if we take 6 members in a consecutive, for this one we need 6 members. 6 consecutive members with least axial force deflections has been taken. These are the rankings we have developed further. And the last one is if we take what are the members with the maximum variation of stiffness. So these forces are compared over here in the case study. So 6 cases have been made. So based on the cases, we have found out that if you look into the graph at the top left, we can see that case 1, which is the case 0, has the maximum deflection because we have taken the least cross section. That is, it is somewhat lesser stiffness compared to the other members, and it has very high deflections. And coming to case 1, it has used the actual bamboo poles. It has a particular reduction in stiffness, and you can see that when we have made the bamboo poles with respect to least deflections, we have observed the least difference in deflections. Least deflections. And when we again go for the member with the least difference in forces, we have a higher deflection, but its reason will be further discussed down. And then the one, even when we have taken the members with the highest possible combination of different stiffnesses, we still have a lesser deflection compared to what we generally make in a simple finite element model. And here you can see the comparison of forces in the second one, compressive force range in the members. So here you can see the first one, it does not have any range of forces between the members. It's because it is basically the same members. And the next one, you can see the case 5 has the least difference between the forces because it is ranked in such a way the members are chosen as the members with the least difference. So coming to the reason why case 5 has the higher deflection compared to other members. So in this case, a further study is made taking the particular poles into 20. We have a deflection ranked based on deflection. So we have also studied based on particular percentile, 20 percentile of the top members and 40 percentile up to 100 percentile, and found out the deflections, how the deflections will be affecting. But still, we found out there will be a variation over here, and the reflection will be further explained down. So here you could see these are the members, and these are the deflection that is observed over here. So you could see that the member with the 12 to 14 mm deflection for the same force is the members which are in highest number. So if we choose members between the group, this will be the member that has the least variation of forces based on the set of bamboos we have. So that's why we have a deflection in a higher range. So in case if we chosen a set of bamboos which has higher, which are in the higher stiffness range, that is least deflection range, we could have a set of bamboo poles with least variation of forces, but lower deflection as well, actually. So this is what we observed from here. So it is not directly taken that, you cannot directly take it that if we choose the members with the least stiffness, difference in stiffness, it will give a higher deflection. It's not a thing that we could conclude it. The reason is that we have the members of higher more members in the particular stiffness range. That's why we have a higher deflection over there.
We're going to have to wrap up soon, Laura. Sorry for that.
Yeah, coming to the conclusion. Yeah, sorry. And here coming to the case 1, in case 1, which we took the least deflections, same cross sections, we had a very high deflection. But in rest of the cases, as I have discussed, we had a very significant reduction in the bamboo pole. So it clearly shows that the scan data could be effectively used compared to directly using measured data and using it, because we have a lot of data, we could directly use it into the analysis model. And coming to the stiffnesses as well, you could see that the members of case 5 has very less deviation of forces. That is, if you see the forces in case 2 or case 3, you have 5% of force deflections. But if you take a least standard deviation, we have only 0.78% of deflection between the maximum forces and the minimum forces. And further coming to the conclusion, that I could also say that the members, as I have discussed earlier, the members lie in a particular lower stiffness range in my analysis, the members which were given to me. So that's why we have a higher deflection over here. But we have a set of bamboos, and if we know which members to be used, we could select bamboos in such a way it has the lower stiffness variation between the members and also a lower deflection as well. We could completely work on it based on this data if we have a set of scanned data of the poles. And the last conclusion I would like to say is that using the exact member properties over here for the analysis, for instance, what I have done in the case study, would be far better than using the traditional analysis method where we use a particular cross section and we use the bamboo pole for analysis. So this would help us in eliminating the sensitivity check, which might or might not give the accurate result. So that's the part. That's it. Thanks a lot.
Thank you so much. Sorry for rushing you there at the end. Very fascinating work. I'll probably privately reach out to you guys soon, because I would love to collaborate on some of this work. I'll ask a quick question that came in from Ashish Nagpurkar. Which softwares are you working with? We saw Rhino and Grasshopper, but specifically for the structure design analysis, which plugins or which other tools are you working with?
We have used Oasis GSA. It has a plugin that could be taken and run directly into Grasshopper, similar to what a Karamba could do, that completely runs in the Grasshopper environment instead of taking it to a different software. And we could also loop it with respect to time. That helped us really a lot here, actually.
Fascinating. It's great to see that Grasshopper is becoming the center of the software universe. All right. Thank you so much, Bharath. Fascinating work. Unfortunately, we're over time. So I'll continue, and the third presenter for today is Dr. Ji Li, who worked as a postdoctoral researcher at Sapienza University in Rome, and then from 2016 to 2020 taught at the Nanjing Tech University as an assistant professor, but currently he's an associate research professor at the College of Civil Engineering and Architecture at Zhejiang University, with main research interests in modern bamboo and timber structures, bio-composite materials, and their probability characteristics. Please, Dr. Li, if you're here, take it away.
Yeah, can you see my PowerPoint?
Perfect. Yes, and we hear you well as well. Go ahead. Thank you.
Because that I'm informed that I can, in this presentation, I can use Chinese. So
yes, just quick reminder to everybody. Yes, we are live translating in 3 languages. Unfortunately, for the audience, we don't have French. So please proceed in Mandarin, and those who want to hear in different languages.
Okay, perfect.
Okay,
gracias, man. Okay.
Thank you.
各位同仁好.
So dear colleagues, I'm from Zhejiang University. I'm Li Zhi. My report is about the light bamboo design and construction based on BIM. The case of residential house in Zhangbei, China. So I will switch to Mandarin. I hope to better express myself more accurately. I also sent the text to our organizers already. So I actually have 6 parts. First part, introduction, and also in the design phase, how I looked into the load numeric number. We're using the city of Zhangjiakou, and in Zhangbei County, here, it's a smaller county compared with the city. It is a high plateau, large wind, low temperature place. So we are giving more robustness, more margin in our design, especially connectors and structural modules. And the location is here.
This is the location of our construction.
the location of the construction. So from the I Ching, we call it a Xun place. A Xun location is favoring wind and wood. So according to Chinese feng shui, it is really auspicious to build a wooden structure. And here, to the west of it, there was a global marathon for solar power modules, widely reported. So we are looking into the at density 7 at a Richter scale for earthquake, the acceleration is 0.1 G. And we are using this foundation to deal with the permafrost of Zhangbei County. This is a very cold place in winter.
Place is -10 to -20, so that we need some specific treatment for the foundation systems. 据说呀，这种螺旋桩基础能够比较好的。
Supposedly, this kind of spiral designed foundation works for the permafrost, and also widely used for nearby PV stations, and also had a minimal impact on the arable land. I'm not really an architect of foundation work, so I can only give you a very brief introduction on this. And also, this is the structure. It is a lightweight glued lamb bamboo, glue bam. The current Professor Xiao Yan from Zhejiang University invented this in 2007. He had rich research experience and also real-life experience. On the right, we are seeing a few real buildings.
Some construction of this type of structure forms, 格鲁班. So if everybody who is interested with this type of structure forms, 大家可以用格鲁班这个关键词去搜索相关的。
Just search glue ban and we'll get the results. The laminated bamboo density is 862 kilogram per square meter, cubic meters. And if you have a secondary lamination, it is still around 900 kg per cubic meters. To reduce the dead weight of the structure, we're using the composite material, bamboo plus wood, SPF, from Canada for the wooden part. Now, I want to talk about the materials. So first, let's look at the bamboo. Structurally, we're using two types of structural bamboo, round bamboo and bamboo strips, unidirectional laminated and a multi-directional laminated bamboo. Of course, they have many other names, depending on where you're from. But just look at my graph, for example, cross-laminated, hybrid bamboo structure, LBL, etc. But in any case, I'm trying to approach this from a mechanical point of view. Unidirectional, which means that the stripes are going to the number two. They're not really standing any weight. Basically, you go through the direction, you cut it, it will crack at the 2 place. And it is easily correct. It's just like making a bamboo mat, and you easily cut it off, either from the perpendicular side or from the pro stripe side. So it's unidirectional. Everything is going through the same direction. But below that, you'll see that multi-directional is like a weaving scheme. And here, you can use XYZ coordinate axis to study the force you put them together, laminate them, or cold roll them, you can make a structural parts, structural modules, and use them in construction project. This is the laminated bamboo strips, the direction of the outward normal to the face on which the stress component acts. A lot of numerical and study results. So this is the stripe without the direction 3, direction 2 stress differences. This is the matrix for its stress elasticity. We need to test for 9 elasticity constants. Of course, we can use other methodologies or structural material study to deal with their stress elasticity and try to figure out the constants. In theory, when you look at the basic elasticity constant of a single stripe, you can extrapolate the stress of resilience of all types of structural modules. These are coming from our publication. Bamboo is a very, very directional in terms of material dynamics. We really need to carefully study it. If we just copy-paste the design philosophy with the wooden or timber and onto the bamboo field, it won't work. Especially when you're designing the connectors and the modules, you really need to think like a bamboo craftsman instead of a lumberjack. And this is the bottom connection system. We have an INBAR with the bolts and nuts. If we only use the INBAR 1 here, INBAR 1, the bolts, plus structural self-weight to overcome the uplift force from the wind load. And also the corner still is to deal with the lateral force from the wind load and seismic vibration. Basically, you have a welding mechanism between the two, and you are being conservative. You're dividing the load force. You're using a very industrial mature connector welding to share the force. And for the second store flooring, it is a lightweight connection system. And here, the 8 millimeter bolt does not penetrate the whole thickness of the truss, which means that we're not cutting it through. Because if we want to cut through the beam, the hole will be perpendicular to XA plane, which will penetrate the laminated layers. Unlike the wood, if you cut, you have a through hole, it won't matter, it won't affect the system. But if you use this, it won't work. So we are using some sidebars to prevent the penetration of the whole laminated beams. And here you have a hole here, but it has 3 laminated layers. And in the middle, we have a hole. And also we have a mechanical drill, and we have STS reinforcing. The reinforcing part will be explained later. Here, we are talking about the shear wall connection. The shear wall is often considered as the most important structural module of a lightweight structure. We have all kinds of study. To put it simply, you can use a shear wall to reinforce the whole system. This is a key sector of study for lightweight, low-rise bamboo buildings. And this is the cold processed corner steel. and also anti-wind uplift system.
Under the roof. 如果前面一直所强调
As shown before, these connectors, when they are being fitted onto the building, we try to avoid anything that may divide or cut the layers of the wood. If we have to penetrate the surface of the laminated structural modules, we will use the wood and the bamboo hybrid panels. So we only drill holes in the wooden part of it. So you can see there are all kinds of connecting mechanisms, and you can calculate the pool or the European yield model to study the force dynamics and the interplay. And definitely is going to be a key areas of study. The next part is main structural components. First, glue band beams. We have a lot of study of this. I will only talk about this project on two areas, in the kitchen and in the toilet. And here you can see this is the kitchen. You need to reduce the height. So the beam will be horizontally placed. It has no stress ability. It cannot withstand any weight. So it's strictly forbidden planarly. And also for this stair place here, the outward contribution is already destroyed. So it cannot withstand weight by itself. So here you have to use some iron bars or iron strips or steel strips to reinforce them. And in the whole construction process, we are using a nailed glue band beam. Very good. And we prevented secondary gluing.
Widely applied in a lot of constructions for this type of. 对，这个是哎呦，然后这个是一些video， 就实际施工的时候。
These are the videos capturing how they installed the panels and beams. And next, I want to talk about hybrid timber bamboo wall. There are 5 advantages as following. First is high bearing capacity, 8 kNmm. Because it's very light-weighted, we combine light-weighted bamboos with heavy-weighted woods. Then 2 persons can complete the carrying and installation process. It's also fire and noise-proof structure. I started this work in 2010 under the leadership of Professor Xiao Yan for more than a decade. These are some papers I published. So far, we believe shear wall is very good future research orientation. In the interest of time, I cannot elaborate on the lab tests. We also use nailed laminated roof. You can see we use 2 boards. We had initial process in Ningbo and also finished the prefabrication material and sent to 2,000 kilometers away in Zhangbei. If you want to make the structure prettier, you can also use bamboos. This is a bird's eye view picture for the completed and finished structure. Finally, we want to talk about manufacture and installation beam platform. In China, if you want to promote any projects, you can always feel the raise of labor cost, like a carpenter. This is a must and a necessary path for China's economic restructuring. If this labor cost is too high, maybe the prefabrication is a very good solution. According to my practices, we believe that due to the features and the natures of bamboo materials in these PowerPoint slides, we can make full use of CNC, mechanical processing, 3D printing to save labor cost. In particular, if we have a large quantity, we can drive down cost. We have different modeling scenarios, different types of softwares. How can we make data exchange? I didn't answer all the above-mentioned questions in my paper. However, I gave a brief introduction about this prefabrication. What I want to emphasize is CNC would play a vital role in the modernized bamboo structure construction. Additionally, we did some modeling and simulation comparison. In particular, against the backdrop of the COVID-19, we can complete this project remotely. If we only rely on the paper version maps, we cannot finish these projects. I think COVID-19 had created very good opportunities for us to promote the BEAM platform. So we change the challenge into advantages. I want to show you this video. You can see the toilet. When I prepared this PPT, wasn't finished. Facade, decoration, and waterproof walls, I cannot elaborate in the interest of time. This project is not far away from grassland. This is a place full of historical legacy. You can see a lot of stars during the night. I believe just like plants, crops, a good structure should be adaptive to the local conditions. I believe our project satisfied this principle. I have two conclusions. First, bamboo material is very good, but should be used smartly. We need a lot of research and experiences before we can really implement a concrete project. It's a teamwork. We need a lot of smart brains to help us to carry out the solid research. Secondly, we need to respect the local conditions. We cannot copy-paste Beijing, Shanghai, and Shenzhen's buildings and structures in Zhangbei area. That would be all for my presentation. Thank you. Look forward to your comments.
Thank you so much, Dr. Lee. I don't believe we've received any questions during your presentation on the GlueBAM. It's fascinating to see the scale at which you're applying it. It's really the future for the material integration. So let's see maybe at the end of the session if some comments pop up. And then in the interest of time, we'll move on with the next presentation by Wei Gao, the Bamboo Gate of Zhangzhong Primary School. I'm sure I'm saying this wrong. But Gao Wei obtained a bachelor degree in architecture from Beijing Jiaotong University before earning a master's degree in architecture from the University of Illinois at Urbana-Champaign. And he has worked at Perkins & Wills in Boston, Archipelago Architects in New York, and the Hotu Institute and other companies. He founded the ADR Studio in 2019, which focuses on the creation of items for rural aesthetic spaces, as he writes himself. So thank you so much, Gao Wei, for joining us. Please share the screen and take it away with your presentation.
Thank you very much. Also, this presentation will be given in Chinese.
No problem.
Thank you. 好 ，OK， 大家好。然后呢，接下来由我为大家分享一个。
Good evening. I will be sharing with you a bamboo structure from rural China. This one is located in the very beautiful village called Jingyun in Zhejiang Province, China. This is a structure after the completion. The total area is not very large, only 300 square meters. The project completed last year. The special feature of this project I want to highlight. This was just an average primary school in rural China under the project of rural revitalization. Together with 128 primary school students, we work together to improve the school gate. Those are the renovated gates. You can see the shape just like a tree guarding outside the school, also located in the main street of this village. This is the main street of this village. Each year during various festivals, all villagers would march through this street. This is not a typical designing project or engineering project. From the very beginning, it served as a teaching project. This is the old school gate. You can see this is a typical structure, maybe constructed 20 or 30 years ago, use bricks and concrete. Other PBL teachers from Shanghai and Hangzhou joined me for this project. Why we believe this is an interesting project? Because it's a PBL modality, project-based learning. Together with students, we would complete the designing while doing the training and teaching. During the course, we will discuss what would be the options for the school gate, what would be the suitable gate for school and for this village. This is very important. We have some baseline studies like soil, bamboo, brick structure, and we had conducted a lot of studies. I was acting as a teacher and telling primary school students what is designing. Actually, they didn't understand what is an architect. I try to use a lay language to tell them how they carry out design work. After classes, different grades students from different grades would come up with different designing proposals. Those designing proposals are from lower grades. You can see very lovely. Those are from higher grade students. They have very good designing descriptions and maps. Sometimes I was surprised, happily, for their sharp observation. For example, this one talk about the tea industry, because tea is a very important element. They also mentioned bamboo. After rounds of discussion with students, we believe the bamboo element had been repeatedly mentioned by various students. For example, this student talk about tea from their village tea garden. We noticed that this school actually had a specific course on tea. And this school wanted very much their school to be so-called transparent. That is, the parents and other people can see, observe children's activity inside the school. Because, their parents normally are migrant workers. They only return back to villages during the festivals or holidays. So they wanted very much they can observe students inside the school. And bamboo is a very popular material locally. And they use bamboos for some inner decoration already. So what's this? This is a musical instrument. It's being invented locally by students and teachers together. It's called the bamboo cannon, musical instrument. They use a kind of a ping pong pad to knock these bamboos, and then you can find the different tunes.
And also in the design phase, the kids were asking me, can we use bamboo to make a front gate of the school? Will it decay soon? Will it collapse? Can we fasten it? Actually, in their mind, they would think it's a beautiful idea to use bamboo to do something, but they're not really sure and whether it actually works. And in our day-to-day work activities, they use bamboo to decorate stuff. Regarding the tea, they run their own tea gardens. In many countrysides places, land is abundant, and agriculture is a very important place to educate. In this school, the teacher and the kids, they love growing things and they incorporate a local life into their work and study. I think that's why they asked me, is it possible to use bamboo to make a front gate? And can we use some patterns inspired by tea? The president of the school, Ma Xingfei, is taking the kids to learn how to bake tea, prepare tea. Maybe they can make a tea house in the school. They can make their own tea and invite guests. They really want to open up the school to the whole county, the whole village. We took some pictures, used the power of one village to nurture one child. So for this school, the kids are left behind by their migrant parents, and all people are their parents. the whole village will become a bigger school campus. So the kids can be nurtured in this very big school and feel proud of their tradition. And when we were designing the front gate, we first studied the older gate. The older gate was shielding people from outside. It's a separation, a partition wall, overprotective, and severance from outside world. It's very, we don't like the message and the image it sends. It's like saying, keep off. It's horrible.
Gate of connection. 在这个里面，我觉得这个校门啊
We want to build a gate of connection. It's not really a gate. In this village, it's a kind of a connecting. And this should be shown in the design and its utility. It should be a gate of connection. So we made the drawing. We finished the drawing. You can see you have several modules. For the original gate, the partition walls used to be a janitor's room. We modified the janitor's room. We sort of cover it with terrace, and it can go to the roof. And the rooftop becomes a tea house. It's connected to the original building. The second part, we have a bamboo structure, the 2 tea leaves. Just like the big trees at both ends of the village. It's like it can show the parents from wind and rain when they're standing there waiting for their kids. And also, this is a slide fence. It can be fully open here. And also, you can see through the gate, the fence. So at any time, the kids can see outside, and outside people can see through. And this curve, its a curve is like a profile of a nearby mountain. Okay. The visual representation, you can see through, and also the kids go in from here. They go into the school, and we added this one too. We hope that it's going to be a tea house, and it's a rooftop tea house. And you can walk down. Basically, you have 3 utility lines for 3 purposes. And this is our design drawing. I really want to thank a local wooden structure company, Anji Zhujing Bamboo Industrial Technology Co. Limited. They provide very strong technology support for every bamboo component. They had cross-section analysis and winding calculation. Okay. Now you can see this is the tea house classroom. You can actually see through from the window. You can see they can brew a cup of tea, and you can see the roof right outside. After making this happen, we had a ribbon cutting. The kids can imprint their hand onto the walkway or the floor, and they're so happy. They're part of this design process. They feel very shocked. Bamboo can really be made into something they love and make such a big front gate. They feel very happy and very proud. It's a kind of connection. Like bamboo or tea is a kind of connection. And later, some already graduated kids, they will come back and see the older school. And also, in a very Chinese countryside, we use very little investment. It's very human-centered design and construction. And you can stimulate people's affinity to their hometown. The kids, they treat it as a product of their own, and they will tell their parents, and this has become a community center of the parents. And you know, we have 3 arcs down below. In winter time, people come here to gather and have fun. And also, if the weather is terrible, they will go upstairs. And also, all the furniture is donated by some villagers, and some were just old furniture. It has become a tea house for the residents. And in summertime, the kids may want to come back to the school to play. They cannot get inside the school complex, but they can stay in the pavilion and read some books and have fun. It's very familiar, and they love it. It is worth visiting in summer holiday. I also want to show you this picture. And in nighttime, it is the most light up place. Some kids, a kid said that I hope the gates can shine in the evening, because in the evening, the whole village is so dark. He hopes we have some lighting. So it's like 2 beacons in their heart. It can shine on their childhood. And for the whole duration of the project design, we worked with the Zhifu Foundation and Sanyo PBL teachers, and very vibrant, dynamic president Ma Qingfei of the school. And we finished the design. We had a lot of good ideas, like the janitor's house. The president, the headmaster of the school, contributed the idea of using the roof of the janitor's house. Okay.
Presentation. Thank you.
Thank you so much. Beautiful project. Must be a great addition to the village. Very nice to see. Thank you.
Thank you.
We didn't receive any questions during the talk again, so we'll keep that for the end of the session. If anybody has any questions, please be reminded to just post them in the chat. And also a quick reminder that we have the live translations in there as well. So thank you, Gao Wei. We'll move on to the final person that I will introduce. And then after me, Professor Seung-Yi Hao will take over in this session. So it's my pleasure to introduce Dr. Mia Tejo-Saputro. I hope I'm pronouncing that correctly, who is an assistant professor at Xi'an Jiatong Liverpool University. She obtained her PhD from the University of Nottingham in the UK in 2018, with her main research focusing on design behavior, augmented reality, and bamboo architecture. She's currently the Digital Design and Fabrication Lab Coordinator at Xi'an Jiatong Liverpool University. And along with her professional practice, she founded Architects Without Borders, a working in progress platform for social missions through architecture practices. Mia, are you here?
Yes, can you hear me okay?
Yes, and we see you as well. Perfect. Maybe hit Control L to go full screen, and then we.
Is it Control L?
Or
yes.
All right, perfect. Take it away. Thank you.
Oh, and right. Good morning. Good night. Actually, good evening. Good morning, and to everybody. My name is Mia. This paper that we actually wrote together, we actually is part of our ongoing series on trying to understand what sort of like bamboo design direction that we are going ahead. So it's really hard to top up all of this sort of like fascinating talk that we just had, and I hope I can try my best and present a bit of a secondary data research related to technological support for bamboo design. Right, not going right. Okay, so just to reiterate our purpose of the research. So we're trying to answer the question of what are design affordances offered by technology in shaping digital bamboo design. And this paper aims to provide a snapshot of the technological support. We did mention about the decade, but actually we looked at 14 different case studies for the last 13 years. And as I mentioned earlier, for us, this is part of the sort of ongoing series in terms of which technological support direction that we are going to be moving forward. And because of the advancement of the technology to facilitate the development of bamboo design and bamboo architecture, it allows us to manipulate form, technique, and fabrication, which was not possible to achieve without the previous digital tool support before. So just a quick literature review. We have noticed, or there are sort of like 4 different uses of technology, main uses of technology for design and construction. First is digital design. It embraces the use of digital media in the design process or architectural design process. In other words, the use of computer tools. Actually, in architectural field, this can be traced back in the 1960s with the rise of utopian thinking, such as the Fun Palace project by Cedric Price and John Littlewood, and the Sketchpad development by Evan Sutherland in 1963. And in 2014, Oxman and Oxman edited a book containing essays about pioneers of this area. The term of digital design is often confused with related terms such as the computational design, which we have seen examples in previous sort of like talk. Computation design, in a nutshell, uses computation and its power. That's the main difference with digital design, to be able to evaluate or calculate the design process, as opposed to merely using digital tools as electronic drawing boards. So Menges and Alquist also in 2011 provide a seminal edited book on computational design when the computational design as a design approach was first conceived. And Caetano et al. In 2020 outlines computational capabilities in comparison with non-computational, which are first automating the design procedures, ability to conducting design tasks and effectively managing large amount of information, incorporate and propagate changes in quick and flexible manner, and also to assist designers in form finding process with the use of automated feedback. The third part is digital fabrication, which is a method uses digital data to direct manufacturing process, which was the definition that provided by Dunt in 2012. there are a few different types of applications that includes the additive procedures, subtractive procedures, and formative procedures. And it also includes laser cutting, CNC milling and routing, rapid prototyping, 3D scanning, and robotics. And lastly, we'll touch on AR/VR technology briefly. This technology have expanded into design and architecture design ecosystem, particularly adding tools to experience and gamifying the design. So Wang and Schnabel in 2008 edited also a book in mixed reality in architecture, design, and construction. And they posit that these new realities merge with or replace parts of the physical world. So in our previous research, we looked at potentials of augmented reality using mobile and head-mounted display, which include augmented co-design studio, assembly guidance system, holographic construction, which is the next focus of our lab's research, and also gamification experience and remote collaboration using cloud-based digital twin construction site. This technology implementation in bamboo can be seen as in one of Christoph's project in 2016, which is spanning over 37 meters, if I'm not mistaken, which is one of our case study, which use computational design informed finding process by using the digital spring particle physics simulation engine, which in turn provide an optimized design before construction started. In terms of different design affordances, in this paper, because we have already written the paper, it's used slightly differently than commonly understood, which is usually understood as close to operations of things. But in this paper, they refer to what the design environment offers designers, focusing on potentials offered by the digital design and computational design tools. In terms of methodology, as I mentioned earlier, this is more a secondary data of 14 studies, which I have the pleasure of Christoph here to his projects and his colleagues' projects are actually one of the most cited or best examples in our area, which illustrate development of technology in bamboo construction. And we use HumanCAD database to look for these projects, and we use keywords such as bamboo and technology. Next slide is the list of 14 case studies that we use, ranging from 2009 to 2020, which this list of projects were found in HumanCAD, HumanCAD database. From these 14 case studies, we did a bit of fun sort of like word cloud, and as we can see here, there's most commonly used keywords are the computational, of course, bamboo, computational, and digital, just to give a bit of an idea on what we are sort of like looking at. As a result itself, from the 14 case studies, from our sort of like observation, we identified that within the last decade or within 13 years, a variety of the use of technology has propelled potentials in bamboo design and architecture, ranging from, the range is quite wide, from the use of bamboo as reinforcement, in case study number 9, for instance, and the use of 3D printing technology to sort of like support bamboo design, and so on. Moving on to the next slide. So in this paper, we also looked at 4 different sort of like types of bamboo development project, which is the first one, bamboo robotic design and fabrication. Within the case study number 1, it looks at development of glue laminated bamboo GLB board structured, assisted by digital tools such as robotic arms and vacuum lamination. And also in case study number 8, the robotic arm is used to aid the bamboo cutting process, which I found quite interesting, and to be able to cut bamboo poles to the required length and cut the required notches for the proposed bamboo resin joint. The second type is the active bending structures, which I think Christoph is one of the pioneers in this area. And we have 3 listed projects, such as case study number 2, which was published in 2021. One of Christoph's project as well provides a novel exploration away from the typical bubble-shaped grid shell geometries to a fluid and elegant continuous surface. And the third type is the augmented and mixed reality, with another example from Christoph's project in 2019, which is in our case study number 5, which required the use of multiple sculptures to actually highlight digital technologies capabilities to stimulate dialogue and foster collaboration, also augmented craftsmanship. Lastly, the last type is we identified from these 14 case studies is the ability to address remote constructions location problem, which is related to case study number 7 and 9, written by the same first author, which is the use of bamboo as part of the solution to the logistical inconvenience on a remote island, and also reducing errors when built with using unskilled labor. Bamboo is used as a reinforcement for an adaptable concrete shell structure, which is the third picture here. And swiftly moving on to the discussion part, we used the lens of digital tectonics, which was taken from Al-Alwan and Mahmoud in 2020. In their sort of like definition, and we classify our 14 case studies looking through these sort of like tools, articulation and assembles tools, by looking at the technical aspect of the design process. Articulation looks at the storytelling of the design, which can provide whether there's a cultural dimension or purely or idealistic proposal, which can create a new value in the cultural view, and assembles, which is quite self-explanatory, which is the assembly process of the building elements, how elements interact with each other. From our analysis through the, in terms of tools, we found that there are 3 different approaches that we can find within the 14 case studies. The first one is the material-driven approach. This approach uses or focuses on exploring the potential of the materials, and it can be seen in case study number 1, which introduced the glue laminated board as a new material for construction, and it uses computational power to optimize the fiber direction and aims to improve material efficiency. Particularly the use of Karamba 3D, which we also have talked about or highlighted earlier for Rhino and Grasshopper plugins, which is used during the form finding process, and to optimize the force situation of tested 1.2 by 1.2 panel. In addition, fabrication process also uses or aided by the 6-axis industrial arm. In this approach, we identify that the design affordances of the technological tools provide physical testing, which is this picture here, to be an integral part of the verification method. Second approach that we identified is the technology-driven approach, which starts with, or is it occurs when designers require to test the technology resources like the software that they have developed. An example that we can infer from our case study is case study number 6. The 3D printed nodes, which is this one, serve as connectors out to scan bamboo poles, which we also have seen earlier in previous talk. From the workflow, which is the next slide, we can see that the first digital model was generated, and then structural analysis was performed on this digital model, and subsequently bamboo was selected from the bamboo stocks, and also they scanned the bamboo poles to be able to update the digital model, and as a result, more optimized sort of like custom 3D printed joints were printed for the assembly. The last sort of like approach that we have sort of like discussed is the multiple loops approach. This is more on the more experimental projects that need more trial and error during each process, and trying to figure out the most optimal model through generation using computer to create prototype and evaluate the design. So our example here that we identified is our case study number 9, which is the bamboo concrete shells. We can see that the looping process, which is the first one and the second loop, through multiple assessments to allow discrepancies between finished outcome and the original design. So parametric modeling and measurement were used to inform the dimension of bamboo reinforcement on site, and which then subsequently being verified on site using the laser rangefinder. So in this approach, we argue that technology provides affordance in terms of verifying dimensions, and the use of augmented reality was also used to guide positioning and to guide direction of the bamboo mesh. The sort of like next part of our discussion is on the articulation. We argue that articulation in each project arises from idea of expanding the possibilities of the use of bamboo and testing it to more experimental shape. And as in our case study number 8, which is the engineering design tropism. But also we want to highlight one of the case study refers to the articulation within the cultural dimensions, such as in the case study number 12, which looks at computational weaving grammar of traditional woven pattern. And we also argue that it might be seen that the articulation in bamboo development in the digital era is closer to the poetic and aesthetic part of it, rather than to the existing cultural dimension. Last from the tools sort of like bit is the assembly processes in bamboo have different kinds of mediums and system. The medium consists of solid surfaces like the concrete 3D printing like resin joints, traditional joints, such as lashing and fabrication like ball joints. On the other hand, we can see the system is conscious of grid system, bending active, holographic ore, and interweaving system. In conclusion, we want to draw on sort of like a brief takeaway in terms of the design affordances presented by technological advancement. They are beneficial in terms of first incorporating traditional bamboo design and build practices. Secondly, also being able to evaluate the complex design. Thirdly, to celebrate the nature of non-standard material to be included as early as this design stage with allowing error and discrepancies, rather than trying very hard to standardize bamboo. Also allowing new bamboo design taxonomy and design language, and also the ability to control the design process in different stages. We want to conclude our sort of like short analysis with this image, or sort of like this diagram, which shows that there are three main parameters according to the digital tectonics that we borrowed: articulation, assembly, and tools. We can infer that both assembly and tools parameters created new possibilities through the use of computational programs for the development of bamboo material for the mainstream construction. So these new possibilities, or this new option, also define new meanings through their shape, method, and systems developed in bamboo material to have a new value in the cultural dimension, which then in turn, that new value can be a new variant or parameter in our articulation part that is justified as the current cultural value. So the cultural dimension in bamboo development is coherent with the poetic and the aesthetic value, and from its current cultural value, much research will occur to increase the value of bamboo itself, and the technological development will keep growing and expanding as in a never-ending loop. So this is our observed future directions in terms of where does this go, or where does technological support in bamboo potentially will go. We will see a continuation of the computational design approach as I think pretty much obvious, and also the more utilization of robotic design approach to mimic or to support repeated bamboo bending processes, or the idea of robotic assisted assembly processes that we are starting to look at. We'll also see more on the holographic construction, and also continue the continuation of the sort of idea of scanning existing bamboo stocks to be translated to digital data. I also want to leave this Mid-Journey. I think everybody is crazy about Mid-Journey, including myself. And this will also, this text-to-image AI, it will also provide a sort of like starting point, especially for younger generations, perhaps, to actually get more awareness of the bamboo design itself. Lastly, we also want to suggest on the pedagogical support for undergraduate program, which I have a great interest in, trying to bring bamboo design or bamboo architecture into undergraduate program. We suggest that bringing bamboo craftsmanship into curriculum in places where bamboo is abandoned is quite crucial, and this can be embedded in our tectonic related modules, aiming at basic understanding of bamboo construction before actually we move on into the technological support. And also an idea to increase awareness of bamboo design by using gamification aspect of augmented reality, which we are trying to introduce as well, using mobile headset. On that note, I would like to say thank you, everybody, to have listened to this short sharing session, and I look forward to your questions and your future collaborations. Thank you.
All right, thank you so much, Mia, and thanks for studying our work. It's always a pleasure to see that. And there's one question that came in from Jim. Are these methods used by any bamboo product processing in China as well, or Indonesia or elsewhere? Sorry, I'm getting some echo. Please mute yourself here in the room. So are these methods used by any bamboo product processing in China, Indonesia, or elsewhere? Are you familiar with micro factory approach for the distributed processing facilities?
Right.
So I guess I'm interested in the application of it. Is this, are the works largely academic, or do you see already an offspring of that in practice or in manufacturing?
Yes, I have to say, I think largely is still academic, but I think in the future this will get it will become more ubiquitous, I suppose, and hopefully we can bring bamboo into mainstream construction soon. And yeah, and in terms of the, right, I'm trying to look for the question. I've actually never heard about the factory approach, the micro factory approach for the distributed processing facilities. So thank you for pointing that out, Jim. And yeah, actually I haven't heard about it.
All right, thank you, Mia. Well, in the interest of time, because we're running behind schedule, let's leave any of the other burning questions for the Q&A at the very end. And then I will pass the floor to Professor Song Hao to introduce our next speaker, Jian Zhang.
Okay, thank you. Thank you very much, Christoph. Yeah, thank you. Yeah, and firstly, I would like to ask all the speakers after, please do keep the time, okay? We have a very strict schedule, so if anybody do not want to sleep in the midnight, please do keep the time, okay? I would very much like to remind you of that, maybe 2 minutes left or whatever. First speaker, then the next session is Dr. Zhang Jian. Kenny Zhang, Director and Chief Architect of the Design Center of Haoyuan Group, Guangzhou Province, Guangzhou City, Guangdong Province. And Kenny has more than 25 years experience in planning, architectural, interior, and all kinds of design works. Today, he's going to share with us his experience in the bamboo bridge in Tall Sands Art Park. Thank you. Kenny, please, the floor is yours.
Yes, thank you. Thank you, Mr. Song. Can you hear me?
Yes, please.
Yes, I will keep my time. So as the other speaker, I will begin my presentation with Chinese. Okay, I've started. 各位同仁，各位
So dear colleagues and dear friends, so I will very briefly share my personal product. I think it's a very interesting bridge. It's in the Fine Art Park. So where is this bridge? It was built in a beautiful landscape, landmark park. Okay, let's go through this very short video so you'll know its surrounding. It's a fine art garden. The whole thing is around a reservoir. We are building a park with different installations and landscaping, some galleries. It's near Guangzhou City. It's a great leisure backyard, as we call it. So it's a very beautiful place. It's very artisty. It's a very arty place. And we have different types of landscapes. And my bridge is inside this place at a critical place. The bridge is a main transport corridor here. It's a big reinforced concrete place. It goes over a wetland, which is going to be a sea of flower. So the bridge is, it just looked too hard for the whole place. And the owner says, is it possible for us to make it elegant? I want to cover it very elegantly. It's going to be an iconic installation in this park. So immediately we think about nature and bamboo to beautify this bridge. This was an early drawing. On the wetland, on the concrete bridge, we have a bamboo cover. And then we developed a conceptual art. The whole bridge is curvy. So the concrete is covered by bamboo. And on the top, we have a curvy roof and some surfaces, so we can beautify the whole bridge. Okay, interior view. We hope it's kind of semi-open. We don't want to make it dark. When you move through the ceiling, you see light from above. We don't want to have an enclosure. We want to feel sunlight and the wind. Okay, structural drawing. First, we wanted to use bamboo. We actually wanted to use bamboo for the whole bridge, but now, we had a lot of typhoon in Guangdong, and the span is more than 100 meters. So we try to be safe, play safe. So the reinforced steel is the scaffold, and then we have bamboo cover on top of the steel structure. The bridge is an important corridor. Large trucks, including firefighter, fire engine, and heavy-duty trucks need to be able to pass through. So we have limitations regarding the width and height of the ceiling. So we are using a drawing software to make the drawing, and then we go to the steel structure company to do the first iteration, and then we finish the scaffolding first, and then we use bamboo. Okay, this is the picture. It took us 2 months, and in the steel modules were prefabbed and installed on site. We started construction in the first half of 2001.
It took us 2 months for the installation of the steel structure. After the steel structure, it comes to the bamboo walls. We want to thank our construction company because they did a good work on the blending and combination between bamboo and steel structures. The inner part is steel, the outer part is bamboo. Originally, we worried about the whole structure would look very clumsy. But actually, you see, it's quite good and neat. We fix the bamboo directly on the steel structure. And the bamboo is very flexible, can bend according to the curve of the steel beams. So you can see the bamboo serves as a cladding to the steel. We use the rope to combine and to bind the steel and the bamboo together. After the first layer of a framework being completed, we enter into the second stage, that is a bamboo frame and the random weaving process. We use diameter 60 centimeters bamboo poles. For the lighting purposes, we use random waving as the inner bamboo mat. It's very similar to the human height. So for the top part, we use larger holes, which means there's going to be more sunlight. For the lower part, we use a smaller holes. Although it's called random waving, we had our structured design. So you can see on the left-hand side is with the inner bamboo mat. On the right-hand side is without. You can see clearly the comparison. You can see the sunshine, very good light. Then it's the important step for waterproofing layer assembling. Outside the external finish part, we had to install this waterproof layer. It's easy for the future's maintenance. But it also posed a challenge because it was very smooth outside. It's not a good finishing result. In order to make the construction more like natural, we use the bamboo to add a few layers. It's just like inner lining mat. The weaving method is to make more sunlight penetrate into the structure. And it's also a rendering effect. So from outside, after adding to this bamboo layer, you will not be able to see this very smooth waterproof layer. It's completely embedded into the nature. So it took us altogether half a year to complete the construction because a lot of labor inputs. I will play you a video clip. You see the finished project. This is a very pleasant sunny day. Very good vision. This is a very long and wide bridge, actually. So the carrying capacity is very good. The heavy-duty trucks and firefighters' vehicles, fire engine can also pass through. No problem with the loading issue. You can see the major frame. With the combination of bamboo and steel, you can find both strength and beauty. There are some joints and knots. You can see we use ropes winding outside the bamboo. Actually, it was an on-site design after discussing with the constructor. During the night time, because the sunlight was very good being captured through this structure. But during the nighttime, actually the light was coming from inside to the outside. So this is a very comprehensive consideration because this bridge is inside a holiday resort. So we must consider this beauty element as an important aspect.
Okay.
Thank you for listening.
Thank you very much. You saved some minutes. And there is a question for you. 有一个 David 给你提了一个问题哈。
David asked a question. Very beautiful bridge. Congratulations. Given that the loads are small, why not make the whole bridge from bamboo instead of cladding the steel sections with bamboo? This is David's question. Because in Guangdong province, very severe typhoon problems. So it cannot withstand the hurricane and typhoon. For the purpose of waterproof, we also need to add a kind of waterproof layer. So if we use pure bamboo, it's not strong enough to withstand the typhoon. If we use old structure as bamboos, since this bridge is very long, 100 meters, it requires large quantity of bamboos as the major beam. If we use 6 bamboo poles together as the major beam, it's not sturdy enough. It's not strong enough. So we had a combined consideration of aesthetic perspective and the withstand of typhoon, and also the loading issue. Because you save us some time, so 2 more questions. The first is why you need to add waterproofing layer. I never seen that in Japan. They use a bunch of leaves cut through roofing in rural areas. The second question is, can you share with us the total cost of the bridge, or per foot cost, or per square meter? 2 questions for you. Thank you. The first question, in Japan, in Southeast Asian countries, they use straws, but they also added the wood panels as the waterproofing layer. Similarly, bamboo, during the rainy season, if without waterproofing layer, it would become rotten. So we need to add a kind of waterproof layer. Initially, we didn't want to add this waterproof layer. We want a more natural structure. But the constructor told us it's a must, the waterproof layer. Otherwise, the maintenance is very problematic. So it's very necessary. For the cost of the bridge, without considering the concrete costs. Let me think about the steel cost of steel frame plus bamboo structure. If per square meter, it's about 5,000 to 6,000 RMB, 5,000 to 6,000 RMB per square meter. Because you use a bamboo to clad outside the steel, how you connect the two? On the steel, we would first weld an iron, and after hot bending of the bamboo, we make sure the bending bamboo is exactly the same as the structure of the steel. Then we can fix these on the steel beam. There's a Spanish question I cannot read, sorry. We will come back to you later, maybe.
The question
thank you
in
anyway.
Spanish is the following. Are there any doubts that bamboo is the vegetable steel of the future?
Yeah, we welcome next speaker, Dr. Wu Ying, lecturer of Beijing University of Civil Engineering and Architecture, focusing on preventive protection of architectural heritage and urban renewal research. Please. Her topic is research on multi-sensor fusion technology for crack monitoring of historical timber structure based on digital twins. Yeah, 数字孪生体. Please. Hello.
Okay, thank you. In order to this presentation will be in order to be could you hear me?
Yes, we can hear you.
Okay, thank you. In order to be explained better, this presentation will be given in Chinese too.
No problem, please. We got interpreters.
Okay, thank you. 今天跟大家汇报的演讲呢，主要将包括以下这5个部分。
5 parts for my presentation. The first part is that the ancient pagoda is one of the important building construction in China. You can see this is a very complicated and stereotyped old pagodas in China as one of the important and key protected structure in China. There are a lot of considerations for these types of construction.
It will create a lot of threats. The cracking, once the cracking continues to grow and combined with the wind load, it will damage the resilience of this pagoda. And the predominant wind is from the southwest. Therefore, we need to reinforce it and look into the wind load distribution. Often we can go to the site to do fluid dynamic analysis, but the on-site monitoring can be problematic. Depending on the cost and the modeling ability and the weather. And the wind tunnel is a very mature study methodology. But for this pagoda, which is so big, it is very tall, impossible to do anything inside the wind tunnel in the following areas. So for the researchers, for the ancient tall pagodas, there's a lack of study. The current modeling simply cannot characterize the feature of wind load distribution on the wooden pagoda. And also the current CFD technology is for the use of modern structure and Chinese-style pavilions. And for this very complicated pagoda structure and the geometric modeling and the mesh separation and the LES and the RANS simulation, they will face a lot of challenges. And there will be all types of formalistic categories, and the current eddy model, whether it's suitable for this high-rising ancient wooden structure, is debatable. Her connection is on and off. Currently, we have a 1:50 ratio, a replica in the wind tunnel, and we try to simulate the wind 1:45 meters velocity per second. And we are taking in the B landscape. The roughness is 0.15 for the surface. And also we have some rough terrain replica models so that we can work out the eddy flow and the wind flow. We tested the intensity of the eddies and the wind average velocity. And also we look at the wind power atlas. They all are in conformity with the design parameters. It has 9 stories, 5 are visible stories, and 4 are invisible hidden stories. And her connection is on and off. And we have a 1:50 geometric replica. We are using the panels chineses to make this wooden replica. And we also streamlined the formation of this pagoda. You can see that interlocking roof supporting beam have different configurations, but we're using a uniform, simplified model to simulate the situation. And also we eliminated the decorative design. We have 511 sensors, test points. The test point, we have a different zoning and a different number and alphabetic number of each sensor. And the sensor hole is perpendicular to the surface facing the wind load. Her connection is off. We can calculate the transient wind load coefficient, which can be used later for the full pagoda simulation, and the calculation of wind load on specific modules. This is a geometric numerical simulation based on the 1991 Beijing Ancient Building Research Center's dataset, and also based on the coefficient obtained in the previous wind tunnel study. Her connection is off, and you can see we have more simplified configuration. We have the roof, cantilever roof, we have the fences, we have the pillars, exterior pillars. In our study, we actually enclosed the surface of each story at the balcony side, and then we imported into the formula. Her connection is off. And also we studied exterior domain of the fluid dynamic surface. You can see H is the height of the building. So we have a 4338 H. We have chosen the 4H from the inlet of the flow, 8H for the tail wake. and you cannot enter the function of the eddy. So we entered the specific eddy power ratio and eddy power. In the CFD, we have a validation of the equilibrium state. We had open field in absence of the building and had open field calculation, and also at the velocity cross-section and the eddy cross-section numeric data and the inflow area, and also barrier-free cross-section numeric data of the eddy. And you can see that numerical simulation profile is in correlating ratio with the eddy profile. And the height here is the height of the model, the replica model. And the curves has a minimum gap with the standardized curve. First, the surface is not movable. The side and the top are the symmetric boundary limits. Inlet, outlet are free inflow, outflow cross-sections. And the mesh, this is the mesh of the surface. This is the mesh. It is by conjugates. And also we have a granular mesh at the contact point between the replica model and the wind flow. And we are able to get the viscous subflow layer at the boundary. The first layer is 0.5 millimeter. You can capture the boundary layer flow velocity. And also you can make sure that the mesh can be independent. M3, M4 are boundary size and dimensions. And when the mesh is getting smaller, the unit number is going up from left to right. The eddy is sensitive to the mesh. To avoid the sensitivity reaction, we have two eddy profile to do a sensitivity calculation. Mesh sensitivity calculation can eliminate dispersed variation under a rough mention and also avoid the situation where a more granular, finer mesh can lead to a spike of the number. Okay, sorry, her connection is on and off, not complete sentences. And also we can the eddy model, the mesh sensitivity, the wind side, the numerical simulation is temporarily close, but at the downwind side, the roughness of the mesh will affect the precision of the numerical simulation number. And the roughness of the mesh can affect the mesh size and dimension. We also calculated 4 mesh models for the eddy. When we choose the M3 dimension, then the calculation error is not changing. And also we had wind load extrapolation. We have 6 eddy modules, the vino average after comparative analysis, we have coupled algorithm for stress and load.
本研究呢提出了从中达到稳定。第二个呢就是
secondly, we have set up the 10-5 residual error and the result and analysis.
第一个分析的是它的平均0度风向脚下迎风面、侧风与背风面的风压对比。
Headwind and side and downwind calculation, we got the wind load pressure on both sides and compare with the wind tunnel parameters.
And
also the comparison at 0 angle, upwind, downwind comparison. Okay, her connection is intermittent. We cannot hear her. And the rooftop, there's a big change of wind load coefficient. From 0.8 to minus 0.75. Because it's at the top has a shielding effect. Right below it, there is a positive pressure zone. You can see that the results of the 4 models are similar to the numerical simulation, and all models overestimated the pressure coefficient. Model 1 and 2 have overestimation than 3 and 4. 3 and 4 accurately extrapolated the upwind pressure. Model 3 and 4 can accurately predict the wind pressure changes at each story and at the rooftop. And also there are fences on each store. And if you eliminate that, you may overestimate the pressure because it has shielding effect. And for the Model 3 and the Model 4 can be used to predict the wind power load pressure on high-rising wooden structure. And Model 3 can accurately predict the wind pressure distribution at the downwind, upwind, and sidewind surfaces. And also, it can provide some numerical standards for the production of this wooden structure. And also for the second floor, there are some damages and the degradation of the structure. So we analyzed the wind pressure at a different angle at the second story. So from the 5th to 8th plane, we calculated the wind pressure from each side.
The result of various turbulence models in D region at different wind directions are compared with those of wind tunnel tests. When comparing with CFD results, actually CFD is more accurate because for TW3 model, it was very accurate. From these photos, you can see the cloud figure. I think we lost her. Of wind pressure coefficient calculated by wind tunnel test at 0 degree wind direction angle. She's on and off. We can see
Coconindo. Coquito.
嗯，同传老师说，那个他的这个网一直在断。
I think we lost her.
听不太好，听不太清。同传老师表示
OK，
就这一段翻译，可能会丢。
OK， 好的，没事。Hello。
Sorry, I think we lost her. Are you still there?
The net connection is not so good. Maybe we.
Hello. Could you
OK,
hear me?
please. 听得到。继续吧。您那边网络好像不是特别的顺畅啊。
Your connection was not very good.
没事。
Sorry. Apologies. So I will continue. This is the analysis, the cloud figure of wind pressure coefficient calculated by using TW3 turbulence model. This is a numerical simulation of the wind. You have only 1 minute.
Please, just focus on that. Thank you.
This is the numerical simulation of the wind, and the average wind speed in each region of the wooden tower varies with the height and position of the wooden tower. So this is the conclusion. First, in the wind tunnel test, the maximum average wind pressure appears in the middle and upper part of the windward face of the tower, while the maximum negative wind pressure appears on the roof. Second, the geometric modeling method for the complex Chinese ancient wooden tower structure is put forward, and the optimized mesh size is 0.01. We compare the 4 turbulence models. We believe model 3 is the best. We also compare the wind tunnel and the inclination, as well as the CFD, flow behavior of wind through the tower. The 3 meters from the pagoda and the result would resume. Thank you for listening. Thank you, Ms. Wu Ying. There are many questions for you. Can you see the chat box? Andrew asked, you use what software for modeling the wind flow? You can answer in English.
Okay, thank you for your question. In this research, we use Ansys Fluent to
Okay, that's the name of the software. Okay.
To describe the wind, and we use BIM to build the印象木塔model.
OK, thank you. 好的，谢谢你啊。他是这个人，请你把这个 软件的名字打在对话
Please
框里。
type the name of the software.
封环境的就好了，并不是这个问题。好，然后那个有一位先生问了你3个问题哈。第一个就是这种方法
3 questions from Jim.
就是意思就是说你这个方法有没有可能用在就是说类似于城市热岛的这种环境里哈。
And this methodology be used on buildings which are not so nature friendly and create more heat islands in urban areas. What type of sensors do you use?
Oh, 就是这可不可能就成为一个就是可以我也不知道冗余的，就是 become AI 我理解这个 ML 我不知道什么意思 AI and ML model for 就是在这个城市环境里啊，如果有没有可能把它做一个什
And
么
this become AI ML model for redundant usage across the cities? Can you answer the question? I try to answer your question. I know these are very technical questions.
I think your question is quite complicated. So to better explain it, I would use Chinese. Maybe we could, maybe if you're interested in my research, we could communicate with you in email. And I put my email on the screen. As time is limited, so I explain it quickly. 刚才说的这个研究关于城市热岛建筑，因为目前我们
with regard to the heat island in urban areas, because we are only in the exploration stage of our modeling, only this model being applied to the pagoda. Maybe it can also be used for heat islands, but we never tried. So if you are interested, we can have further discussions.
这是第一个。然后第二个，刚才提到的就是关于这个传感器。然后我们这边的传感器
About the sensors.
映像木塔它非常的复杂，涉及到的内容
Because a pagoda is a complicated structure. So we reach out to other famous companies in China. For example, China Cultural Heritage Research Institute, they provided us the sensors. So I cannot give you a definite answer on the sensors because it's from our partner. You can send me an email and I will share our experiences later on. Thank you.
Okay, we'd like to invite next speaker, Ms. Brianna Katrina Husinger from University of São Paulo, Brazil. She's currently a Master of Science student at the University of São Paulo in Sustainable Building Technology with thesis entitled The Development of Bamboo Architecture in Brazil and Possible Design Strategies Capable of Enhancing its Use Nationwide, just across Brazil. And also, he got a lot more chances or experiences working in the most inspiring architectural institutions in Brazil, focusing on sustainability, and also founded her very own architectural practice. Oh, great. In Brazil, where she has designed and built acclaimed and published eco houses. Yeah, please, Brianna, the floor is yours.
Thank you very much.
Yeah,
I'm going to share my presentation.
Yeah, please.
Hi, Brianna. Just saying hello. Good to see you.
Hello, Christoph. Nice to see you. I would like to thank the opportunity to speak here and represent Brazil and my university, University of São Paulo. And I would like to also thank my teachers, Cláudia, Fernando, and Arthur. And also Christoph, he visited Brazil this year and I was able to participate in his course, and he opened up a whole world of parametric design with bamboo for me and for other Brazilian designers as well. I consider myself to be a world citizen, so I am Brazilian, but I am also a natural born traveler. And I have had the opportunity to work as an architect, designing and building with bamboo in several different parts of the world, from Indonesia to Australia, India, Nepal, and now in Brazil, where I build, and I am also an academic researcher. What I can say from this experience is that we cannot identify a one world bamboo architecture. Each country holds its own style derived from a combination of available designers, skilled labor, and material. Bamboo architecture is sustainable and responsive to context. So here we have a couple of bamboo buildings in Brazil, a panorama, and Brazil is very unique. Civil construction here works in a very peculiar way. It is dependent on human relations and mostly empirical knowledge. We do not have a historical approach to bamboo, and it is not included in our social fabric. The positive side to this is that it does not carry the stigma of being the poor man's timber. But how do we build with such a complex material such as bamboo? There is a lot of trial and error, but somehow we figure it out. Slowly and steadily, we have been implementing measures to make bamboo construction more accessible. This is due to the fact that bamboo is widely available in nature and is a low added value material. In a spontaneous way, small suppliers have been appearing in a distributed manner. It is possible to buy treated bamboo poles almost everywhere in the country. In addition to this, we have a recent norm on bamboo structures. Our norm entails projects, bamboo projects, and bamboo physical and mechanical properties. It is a norm of 2020, so it's a very recent norm. What are some of the biggest challenges we have to face to increment bamboo architecture in Brazil? We don't have a clear architectural identity. There is a big gap in qualified labor. The existing qualified labor is expensive and almost inaccessible, and this is due to the lack of cultural and historical approach. So how can we face some of these challenges? It is possible to tackle all these topics if we draw concepts from our architectural modernism experience, our very successful experience. In essence, if we take advantage of this, such as using whole cones, whole poles as specified in our norm, and designing constructive systems that define the form and also focus on detail. So to illustrate these principles, I have chosen to show you the building Amanaki by architect Leiko Hamamotomura. This building is situated an hour from the city center of São Paulo and functions as an outdoor classroom. There is an amazing span of 16 meters that allows for a seamless integration with the beautiful surroundings. The bamboo spatial truss is made out of 254 moço cones and is a repetition of 3 rows and 9 columns of a square-based pyramid with a 2-meter edge. The joint is made out of cement mortar as filling and a steel rod connection from the inside of the cone connects to the outside of the cone. Literature tends to separate bamboo joints in two parts, traditional and modern. In spite of the fact that this joint in the Amanaki building is a modern joint, its execution is very time-consuming. Each connection is manufactured manually. Each pole is filled with cement mortar twice. The curing process is around 28 days, and each extremity of each pole has an outside brace to avoid shear. There is a difficulty in assembling the inside rod with the outside element because of the dimension variability. So, by reverse engineering the tectonics of this connector and applying parametric design to it, I believe it is possible to address certain time-consuming aspects in the construction aspects mentioned above. So I initiated the study by form finding in Rhino, and the sub-D command was very useful to this. And it was possible to understand some of the complications faced during constructions, and that could be faced if this building was built in a parametric way. So I began prototyping and some testing with materials other than bamboo. And if each leg of the connector has a parameter that defines a different diameter, they could fit perfectly into each comb, even if each comb of the structure has a different diameter. And then we could eliminate the cement mortar filling, the braces, clamps or screws or other elements to the structure, and ensuring structural continuity between the connections and the bamboo. And there's an example from Ars Villa-Lobos that shows us that glued fittings are perfectly suitable for bamboo spatial trusses. So this was a reference to be able to develop further the connection. So next steps in this study would be scripting in Grasshopper, continue to prototype in different materials that could be 3D printed and possibly glued to the bamboo, and see if in fact if we use high design and parametric design, construction would be less time consuming and more approachable, not only to the architect, but also to the builders. And I believe that expected conclusions would be that low and high technology could be combined and used as a tool to overcome skilled labor constraints and create a new trend and possibly an identity in bamboo architecture in Brazil and also in other places in the world. And I would just like to finish saying that I was very impressed by Mia's case study number 6, where I find it's very close to this thought process. And even though we are in different parts of the world, we are thinking very much alike. So thank you very much for your attention.
Okay, thank you, Brianna. Thank you very much. Any questions? Just let me say.
Excuse me, Professor Song, that I have a simple question.
Please.
I just wondering, you say that there is a very beautiful bamboo truss, and then that we see the roof. So how the roof connected with the bamboo truss? This is my question. Thank you very much.
Mm-hmm.
The roof is also made of bamboo, and they are connected, but they are two different elements. And they are also connected by bamboo.
also collected by bamboo, by the use some carbon to collect them. Okay,
exactly.
Thank you.
Okay, one more question from Jean. How open is Brazilian government and the local MSMEs industry for agroforestry or bamboo processing?
So we are beginning now to have some government incentives for developing bamboo production towards, especially towards paper fabrication. But not towards bamboo as a civil construction material. However, independently from the government, there's a lot of research in academic institutions, and there are a lot of bamboo people, like passionate bamboo people that develop their own practices and their own supplying methods.
Okay. He mentioned MSME means micro, small, medium enterprises. Yeah, small firms. Okay. Okay, thank you. Okay, if no questions, thank you very much, Brianna. Yeah, thank you. So next speaker, Esti Nudia. Sorry, Nudia. Yes, Nudia. Yes. Esti Nudia is a postgraduate research student at Sheffield School of Architecture. The research topic for her PhD study is bamboo for great shell structures. Before studying at University of Sheffield, she has been teaching at Department of Architecture, Petra Christian University, Indonesia. For her research and study, she is funded by the Indonesia Endowment Fund for Education, which is a scholarship from Ministry of Finance, Republic of Indonesia. Okay, the floor is yours. Yeah.
Okay, I will. Thank you very much for the opportunity. I'm going to share my screen now. Okay, can you see it?
Yes, yes.
Okay, once again, thank you for the opportunity, and I would like to present my research project as part of my PhD study right now at Sheffield School of Architecture. And this research is not complete yet, so it's still ongoing research. And this one is part of the whole thesis. And my big topic is about bamboo for grid shell structure, especially the utilization of Indonesian bamboo for grid shell structure. So during my first exploration about bamboo in Indonesia, bamboo has been used extensively and also has been part of our daily life. And bamboo in building has been utilized in vernacular architecture for many centuries. And even though a decade ago, people tend to perceive bamboo as material for temporary buildings or for small-scale buildings, right now, the development of bamboo architecture in Indonesia is emerging and become popular and more popular. As we can see from this picture, more and more buildings built using bamboo, and some of the buildings span over a wide space and also used for a lot of multi-purpose and communal activities. The first picture is a gymnastic stadium or built using bamboo grid shell in Green School, Bali. And the second picture is Obi Great Hall. And the third picture is the 5-element resort at Bali. So I do a research on particularly grid shell structure because I saw that grid shell is an effective structure system. It is a shell structure, but consists of straight member. And if we compare it to the solid shell structure, grid shell needs less material than the solid shell structure. And when we utilizing bamboo into grid shell structure, as we know that bamboo is a very sustainable material, it can enhance the material efficiency for the structure. However, as we already know from from the previous presentation, also state this about how very the material properties of bamboo, and also how bamboo is really difficult to standard even, and also even in the one poles on one comb, bamboo has a very diverse material properties, anatomy, and also form. Therefore, the objective of my research is I want to analyze the structural behavior of grid shell through computational and also finite element analysis, and then compare it to the by building a full-scale model. So the method for my research, I divided the three key elements here into the material, and also construction and form and forces. For the material, I did a series of material tests, which is including 6 items of material tests: compression, shear, tension, bending, both parallel and also perpendicular to the fiber, and also tension perpendicular to the fiber. So I can gain the modulus of elasticity for the material properties that parallel to the fiber, and also transverse material properties. And I'm going to use the material properties into the simulation, which is including form finding using rhinoceros and also grasshopper to find the form, and then structural analysis using finite element analysis in Abacus. And then I built a real scale model or full scale model in Indonesia. So during the design process in rhinoceros, we found that it is quite unlimited on how we design the grid shell. We can inflate the grid shell and also form a high curvature. It's really free, a huge freedom for us to make it into a very high curvature or lower curvature. But basically, the main question is the next step after we design the grid shell. How we build the grid shell using the bamboo? Can we bend the bamboo into the desirable curvature? Or will the bamboo break at certain point when we bend the bamboo into this kind of form? Actually, it is also a common practice in Indonesia to bend the bamboo by slicing it. But if we decide to slicing the bamboo, I'm sure it's going to reduce the strength, and also practically the loads will be bare only by the thin strip, and it's really prone to splitting and breaking. So in this research, I did the construction process using full calm bamboo and also bamboo split. I'm going to present it using a video, the process. Before we construct the grid shell structure, we did a simple experiment by bending the bamboo on site. So we are using rope and also fire, and we found, and we estimated the height of the curvature when the bamboo start breaking. And then we try to naturally bend the bamboo and build it into a full grid shell structure. We managed to build a model using full calm bamboo with dimension of 10.80 meters. And the height only reached around 1 meters and 10 centimeters, so 110 centimeters. So it's quite narrow. But I think if we expand the dimension, we can reach higher curvature. And the next model is bamboo split. We test using bamboo split because I want to know, or we want to know about how it's different between the bamboo comb and also the bamboo split. So as we know that bamboo split is more flexible than the bamboo comb, we start splitting the bamboo and then make it into a grid and then inflate the grids into and form a grid shell. And we managed to build like 840 centimeters dimension, and the height only reached 240 centimeters. We cannot push, we cannot reach higher because, as we saw from the previous picture, that the bamboo at the perimeter starts snapping. That means that's the limitation that can be reached by the bamboo. After that, I exported the model to the Abacus and doing two type of simulation, model 1 using bamboo comb and model 2 using bamboo split. Previously, after we built the grid shell model, we imposed the load there. So we also calculate the displacement or the deflection of the bamboo. And then from the FEA simulation, beside we doing the stress distribution analysis, we also measure the displacement or the deflection. So the first scenario, we impose the load at the center. The second scenario, we impose the load at the vertical or horizontal line. And the third scenario, we impose the load diagonally. And then the fourth scenario, we impose the load asymmetrically. This kind of imposing load, also we did the same scenario to the real test or to the full-scale model. From the model 1, we found this kind of stress distribution, and also we calculate the displacement. And we can see that it is breaking. And in reality, when I did the real test, the grid shell structure was breaking and collapsed. So I couldn't do another test because the structure already collapsed for the whole count model. I found from the measurement of the displacement that there is a vary or discrepancy between the deflection or displacement between the simulation and also the real test or the full-scale model. And from the second model, the model wasn't collapsed at the time, and I managed to did all the 4 scenarios and found the displacement from both the simulation and also the real test model. I also found a quite huge discrepancy, like from the real test model, the deflection can reach around 6 centimeters. But as we can see here from the FEA simulation, the result is quite small. It is in meters. So the units is in meters. So we are still try to figure out like the ratio with the difference between the real test model and also the simulation. And we think that it is quite possible happen because, as we know, bamboo is very having a very large variation. It is tapered. And even though we split bamboo and we try to make each member in the same dimension or size, we still cannot control whether the size from this point to that point will be similar. So that kind of variation is quite difficult to determine or to input it into the simulation. So I think it is something that we still try to figure out about how the discrepancy and also how big is the ratio. So from our first conclusion, we conclude that the constructional constraint of bamboo lies on its curvature. Like when we want to use the bending active structure for grid shell using bamboo, then first we have to figure out the depth of curvature of the members. And also we have to be careful for the joining system. Like I made several mistakes for the joining system during the construction process. And it happened, some joining system fail because of buckling and also splitting. Therefore, when designing a grid shell structure, we have to consider curvature as the control variable. And for the next step, for the next step of my research, I will deepen the analysis of the simulation to find the discrepancy ratio. And also, I hope that the result or the outcome of my research can be a guideline for designing a grid shell using bamboo. And not only that, we really hope that we can be implemented in design and also construction of another structure using bending active bamboo. I think that's all. Thank you very much for the opportunity.
Thank you, Esti.
Yeah.
Now we just come to the question and answer. If any questions to Esti, please, Christoph, it's your floor again.
I have some.
Let's go ahead, Dr. Lee. Go ahead.
Yeah.
Because I think this is a very interesting topic, and happening that I have something also made in bamboo. Just when I can look. Yeah, so
thank you.
You can see here are some details that for these small things, you use bamboo to form a curvature. You can see here that he used some fabrication. Use bamboo strips to cross with each other to form it to be a panel can bearing force at multi directions. So my question is that during your design, that when you want to build some roof or how to say the roof structures, that how do you solve the problems to make the roof can bearing force not only at this directions but also at its transverse directions? This is my question. Thank you very much.
Okay, actually for the nodal connection of grid shell, we have to make it quite loose when we erect the grid cell, but then we have to stiff the connection when we reach the desirable form. So for the full-scale model, the process of building a full-scale model, we try several type of connection. So we join the nodal connection using rope. Or using wire for the bamboo split. And finally, for the bamboo split, we decided using wire connection. Because it is possible for the member to rotate during the construction process.
Yeah, because for my experience, that if we just use layers, that is very easy to get a splitting finger. It's not so good for use nails that in this type of structures. Maybe use something to rotate, maybe much better.
Yes, I'm using rope, but as I mentioned before, when I built the full calm model, using full calm bamboo, at the perimeter, I'm using a screw and also a fixed connection, and it's make the bamboo split.
Because for our structural engineering, a lot of problem is that if we use some weird connections, it's going to be very difficult to calculate it. How to calculate it is going to be a lot of problem that it's more like spheres.
Thank you.
Okay, whatever. Thank you very much. Thank you very much.
You're touching on some very essential challenges of making bending active grid shells. But the shear force needs to be kept free, but the translational forces need to be locked in. There's within Cantonese bamboo scaffolding techniques, there's quite a few knots that allow for that. So they have different knotting techniques that still use the different profiles of the bamboo to prevent them from sliding over each other, but still allow for a hinging. And there have been some experiments done by colleagues in Taiwan where they, for example, start to work with these pre-made hoop hinges as well. But they all come with their own defects. You need to be able to absorb different bamboo diameters, and then you need to prevent the local buckling at the connections as well. But as Esti was saying, also looking at the Friotto work, by anchoring the foundations edges of the shell and by adding diagonals through it, you're basically locking in the geometries, the triangular shapes, and that provides you a stable shell as a whole. But the calculation of it, luckily, you're right. It's a very difficult challenge.
Yeah, I think that especially for structural engineering, is that we have to develop some equations to to calculate it, then that is can be accepted by the design stands. And then
the problem is with a hand-tied connection, that the craftsman himself already has a huge impact on the strength of the connection as well. So it all exacerbates and adds on top of each other.
Yeah, so maybe that, as you give us, for example, maybe use the metal hoop connection is going to be a solution that it's become to a design for the steers much easier. Okay, thank you very much. Thank you very much.
There's another question in the chat. Oh, sorry. Yes, go ahead. Esty, go ahead.
Okay, thank you for the feedback from both of you. And then I think also it's still in a discussion process between me and also my supervisor because of the connection. It's also we need to input the connection in the abacus. So what type of connection, and and also from the building the full scale model, I learned from the mistake that I made before, and then it's going to be quite good feedback for me, I think. Thank you.
There's another question in the room from Ashish Nagpurkar. What difference in structural strength of bamboo do you have when you use split bamboo versus full columns? Nice presentation, Esty.
Thank you. Yeah, the structural strength for the bamboo, if we use the split, it's completely different because the sectional area for the bamboo split is smaller than the bamboo column. If we talk about the strength of the bamboo itself, but for the finite element analysis, I'm using the modulus of elasticity of the bamboo. So it's quite applicable for both the bamboo column and also bamboo split. And I did the material test. So I did the test like compression, including bending tests, before doing the building of the full scale model, and I use the result from the material test as the input parameter for the abacus. And as bamboo is anisotropic material, so I also consider the modulus of elasticity of the material that is parallel to the fiber, and also the transverse material properties. I hope that's answer.
Yeah, as the moment of inertia changes dramatically if you go from a round section to a split, so immediately the deflections go up a lot. I see a brave person raising his hand. Juan Manuel, maybe switch on your microphone and camera, and you can ask the question live. Juan Manuel, I see you have your hand up. And I saw you for a split second there.
Dentro del tema, entendiendo la forma de la estructura como tal.
Regarding the shape of the structure itself, I would like to know what's the maturity state of the material that should be used. When should you use the bamboo? I'm in Colombia, and the material varies widely. But what's the maturity state that you use for bamboo? Thank you.
I'm sorry, I couldn't understand the question. Probably the interpreter can help me, or?
Are you listening to the English translation?
Yes, we were. I was too, and it was a bit hard to grasp the full question. Could the interpreter maybe quickly repeat?
Can you hear me now?
Can you hear you? The line broke up for a second. Thank you.
All right. Can you hear me, Esty?
Yes.
Esty, can you hear me? I think Esty is not on the channel. Please switch. Can you ask her, please, to switch to the English channel?
Esty, can you switch to the English channel, please? Or are you hearing the translator talk?
Which language should I choose? English, Chinese, or Spanish?
Please choose English channel.
Okay.
Please choose English channel so you can hear Thomas. He had translated it into English.
Esty, can you hear me now?
Yes, I can hear you.
So Esty, the question that was asked was about the maturity of the bamboo. When in the maturity state of the bamboo do you use it? What's the maturity state that you choose?
The age of the bamboo. How old does the bamboo have to be to use it?
What you mean, the material state? Is it about the
maturity?
drying?
How old?
I'm sorry. So I'm used bamboo 3 to 4 years old because I think from the literature review and also from based on the experience that the optimal age of the bamboo to be used for the construction.
Okay, thank you. I had an earlier question from maybe one of the other speakers. Maybe we can open up the floor to some of the other speakers as well. There was a question for Bharath by our colleague David Trujillo, how he is modeling the connection slippage, which relates to the question that was just asked to Esti as well. I don't know, Bharath, if you're still with us?
Yeah, I'm here.
Great.
I have not modeled any connection as a particular connection. We have modeled it as a pin joint actually in my model. So I have not considered the slippage and things into it. It was basically a study about only the actual properties and how it would be selected. So we have not gone into that.
Okay, thank you.
Okay, great. Thank you, Bharath.
Thank you, Bharath. Thank you. I will consider it.
It was more a general question. Okay, well, we are half an hour over time. It's a fascinating topic. I'd love to talk with everybody for another half hour, but we do have to wrap up, unfortunately. Professor Song, you wanted to rally up the troops for a group photo?
Oh, yes, please. Miss Jing. Hello, Jingwei. hello, yeah.
Good morning, good afternoon, and good evening to everybody. It's group photo time. Thank you for all the participants and all the panelists. Thank you for your participation, and we had a very hot discussion. I think a very good session here. And we have registered many participants. So I want everybody now to turn on your camera. Please, and we can have a group photo. We finally could have a global time now. Jorge. Okay, okay. Now I have 4 pages of people, so let me go one by one. Let me go one by one. One,
popular session.
2, 1, 2, 3. Smile. Okay, now go page 2. 1, 2, 3. Separate. Smile. Okay, let me go to page 3. 1, 2, 3. Thomas. We should include our interpreters here. Well, they had made this session possible. We should say thank you to them. It's quite challenging for them, I think. Quite challenging time tonight. Okay, again. 1, 2, 3. Okay. Brianna has the brightest smile. Okay. 1, 2, 3. 1, 2, 3. Oh, a lot of people cannot open their camera, but I have you. Don't worry. I have you in my picture. Okay. Thank you.
Yeah, thank you. Okay. Last but not least, please don't forget next session on next Tuesday. Same time. Yeah, very much welcome. Okay, see you. Bye.
Thank you so much, everybody. Have a good night.
Have a good night. Hi, Christoph. Nice to meet you here.
Good night. Good day.
Yeah, good day. Good night. Bye.
Bye.
Good night. Bye.